Course. Hi, Sayan. Stefania.
Hey, hi. Hello. I think we'll give it a minute and some 5 minutes and get started. Okay. Yeah.
Hey guys, we'll start in 4 minutes, 4 to 5 minutes. Just wait for the other guys to join us. Hi, Sayan. Can you hear me?
Yes, I can hear you. Yeah. Yeah.
We'll
So
start
I think we'll
shortly.
just give it a minute and get started here. Okay.
Yeah, we can start at 8 o'clock because we
Thank
mentioned
you.
8 to that.
Yeah.
Hi guys, we'll just start in the next minute or two. I think people are just joining in because we mentioned 8 o'clock. So maybe by 8:03 we will start. Is that fine, Sayan?
Yes, I'm fine. No problem.
Okay, you just wait. Start in 2 minutes by 8:03. Hi everyone, welcome to this live session. Sayan, are you ready to start?
Yes, I think we can start. No problem. Yeah.
Great.
Yeah.
So yeah, over to you. You can begin. Welcome everyone to the first live session. This we're going to be starting a series of live sessions wherein we're going to be working through a project together. So today is just the introduction where Sayan will be working through a few different things with us. So welcome everyone, and we hope you're looking forward to the session. Over to you, Sayan.
Hey, thank you. So once again, I wish all of you a very good evening, and thank you for your time for uh, you know taking time out of your busy schedule and coming for the session. So we're going to make it. It's going to be a very generic session. We're going to talk about lots of things, starting right from our data science life cycle. What are the things we need to do, and obviously, as we look into the project, what are some of the steps to be done? Kind of a recap of all the pieces you have gone through in your curriculum, starting right from the problem statement to statistics, inferential stats. What are the areas where hypothesis testing needs to be done? And obviously, what are some of the things to look out for in the model building phase? We're going to go over the entire life cycle, and finally, if time permits, I'm actually going to show you a couple of uh, a few other things on how to deploy productionized models, because that's another aspect that I see is very important. It's one thing to build your models, but it's also very important for us to know how to productionize our models. So we'll probably keep some time aside towards the end to discuss a little bit about that. So with that, I'm just going to quickly take a minute and share my screen. Just give me a quick second here, guys, while I quickly set it up, and we'll get started. All right, so I'm just going to be quickly going ahead and sharing my screen with all of you. Please do confirm to me on the chat window if you're absolutely able to hear me loud and clear, and if all of you are able to see my screen. And please do keep posting on chat. So I have a parallel monitor opened up, and any kind of questions I'll be very happy to address right then and there itself. All right, cool. Thank you so much, guys. So one thing I would really appreciate, so if you have any doubts then and there itself, you can absolutely ask me. So no worries. But if there is some other Any other generic doubts if you have? So maybe I would appreciate if you can. We'll have a Q&A session towards the end. So any generic questions, which is aside from what we are discussing there and there, we'll probably take it up at the end. So that's just to maintain the overall flow of the session. But yes, absolutely. As and when I'm discussing some of the concepts, if you have any questions, I'll be very happy to take it up there and there itself. So feel free and let's make it a very interactive session. So as I said, keep asking lots of questions. Anything that you have in your mind, feel free to ask me. But any generic questions which you think is little out of context, if you have anything on deep learning and stuff, so all of those things you can keep aside. We'll take it up towards the end of the session. All right. So we will go ahead and get started. I'm very sure some of you, I'm not sure if you know me, if you have interacted before, but just a quick introduction about what I do. This is a quick LinkedIn profile about myself. I'm very sure you probably a faculty profile has been sent across to you. So this is a quick introduction about what I do. I've been involved in this space for around 8 years now, and I have worked for 4 companies in my career. I'm involved with a lot of organizations on training assignments, on consulting assignments. I work as an independent consultant at this present date, and obviously I'm tied up with Upgrad on some of their trainings and content delivery. As and when some of these interactive sessions keep on, I'm pretty much involved with Upgrad on these sessions. So looking forward to interacting with all of you. Now, coming back to where we are, and I believe all of you have gone through the program, all of you are aware of some of the concepts. So first things first, we've gone through the basics of data science. So what I'm going to do is I'm going to take a quick minute to run you through what we are going to be doing through our sessions, and obviously through the entire project. We're going to come to the project, exactly what we'll be doing at the later end of the session. We're going to be introducing the project to you. We won't be doing anything about the project today. It will be a very generic session. Now, the first things first, we have the problem statement. All right. So this is just a quick run through on what you already know. So initial 5 minutes we'll spend on what you already know. Probably you've seen this before. And if not, this will be a little bit of an additional thing that you can get out of this. So first things first, you will have to be very clear on what the problem statement actually is, right? Remember, this is a very crucial phase of the project. Obviously, without requirements, you cannot approach anything in the data science project. And as I talk about the problem statement, I also want to take a quick minute to give you a basic difference between the framework from which we approach a typical data science project and the typical framework from which we approach a typical statistical project. So oftentimes I get asked this question. So what is the difference between classical statistics? Because you would have gone through an inferential statistics course in your session, and you would have also gone through data science. So many times people ask, okay, inferential stats also we are doing predictions. In data science also we are doing predictions. So what is the difference? All right. So I want to take a quick minute to address this part with all of you. So we have inferential statistics on one hand, and we have data science on the other hand. And by the way, as you're attending this session, I hope all of you are absolutely clear on where data science fits in. When I talk about data science, your AI, your machine learning, your deep learning, all of it comes as part of it, right? So I believe everybody is aware of this bucket, and I'm assuming all of you are aware of this bucket, that when we talk about AI, your machine learning, okay, let me put it this way. So when we typically talk about AI, so the entire bucket here is that of data science. Your artificial intelligence is pretty much a part of this bucket. Your AI comes as part of this bucket. Your machine learning is a kind of AI, and your deep learning is basically a subset of machine learning, right? I hope all of you are absolutely clear. So going forward, when I take references to this, I'll be talking about data science. I won't be really talking about AI, machine learning, deep learning, because they're ultimately a part of the larger data science canvas, right? Because even if you think of the most advanced form of deep learning based AI, which is the self-driving car, we are basically talking about basic data science. And what is data science at its very core? We are looking at lots and lots of raw, dirty data and how we can generate insights or information around raw data. If you think of a self-driving car, what is a self-driving car doing at its very core? It is gathering information, it's gathering dirty raw data from all its sensors. It is capturing raw, dirty data from all its sensors, and it is converting that using algorithms into information or insights, and those insights are basically used to take decisions. What are the decisions the car is making? Constantly the car is evaluating whether should I take a right, should I take a left, should I go slow, should I go fast. So it is very core. Even a more very advanced form of deep learning based AI, self-driving car, is effectively an example of data science solution. Okay, so just wanted to be absolutely clear on what this particular hierarchy looks like. All right, now coming back to the original discussion on statistics, let's come back. Let's take a quick minute to talk about this. And this is very important. Why am I talking about this? Because we are talking about the problem statement. So statistics, and specifically, we are talking about inferential statistics versus data science. So what is the difference in the approach? So anybody would like to contribute to this? Anybody would like to answer this? Let me just hear out from all of you. What do you think is the difference between inferential statistics? There also you're making a prediction versus data science. Here also you're making a prediction. So all the models that you've built in your in your session so far, at the end of the day, what are you doing? If it's a regression problem, you're predicting some numerical output. If it's a classification problem, you're predicting some categorical output. So how is inferential statistics different? In inferential statistics also you would have made some predictive predictions, right? So you have some sample data. Based on the sample data, you're trying to estimate what is going on in the population, right? So how is it different? All right, doesn't have evaluation metrics. Okay, let me clarify, Madhu, to answer that question. Actually, let me clarify, even hypothesis testing, you can pretty much create a type 1, type 2 error table. I'm very sure you guys have gone through hypothesis testing. And just to kind of clarify that part, again, I encourage all of you to participate. I appreciate all of you participating with your answers. There are no wrong answers in the session. Okay, the only person who can go wrong here is me. So absolutely feel free. There's nothing to be afraid of giving wrong answers. Just to clarify, we are all learning here. So the idea is in inferential stats also, we are pretty much generating a hypothesis testing error table. And I'll give a simple example here. I'm very sure you have seen this before. It's very much like your confusion matrix. The table is very much like your confusion matrix, right? So what do you have in the confusion matrix? You've got predicted value. You got predicted, you got actuals. You got predicted, you got actuals, right? And your hypothesis testing error table pretty much looks like this also. So only difference is in hypothesis testing, when I say predicted, is basically the hypothesized value. This is basically what you are getting from the hypothesis test. This is your hypothesized value. When I say actuals, that's your actual value, right? I'll give a simple example. Let's say predicted 0, predicted 1. Basically, it means first case could be null hypothesis true, and then you're basically saying null hypothesis false. And second case could be actuals could be, the actual could be, so I'm just creating some space here. The actual could be null true and null false. And there goes a table very much like your confusion matrix, which you have seen in the classification problems, right? So even in inferential statistics, just to answer that question, you pretty much have a metrics table here as well. Okay, so you will do your usual hypothesis testing, and the results of your hypothesis testing you can pretty much summarize in this particular table format as well, just to clarify. Okay, this works exactly the same way as your confusion matrix, where you have your type 1 error, type 2 error. The concept is very similar. All right, now, so what is the actual? Let me read out some other answers that you've given me. Predicting about population based on sample. That is correct. That is basically the definition of inferential statistics. So, that's absolutely correct. And okay, I think that's getting into something else, Keshav. Gradient boosted. I think that's very different. Let's not get there right now. I think that's a very different thing. So we assume data is supposed. Okay, we assume data is having a predefined distribution. I think that's also a very good point, Keshav. I think classical statistics always makes assumptions. Very good point. I want to take a minute to talk about that as well. Classical statistics, all the classical statistical techniques you have learned, like even linear regression, logistic regression, all these algorithms will make some basic assumptions about your data. Okay, but in the advanced algorithms that you would have learned, like probably you would have learned random forest, you would have learned ensemble techniques, and some of the other advanced algorithms, like even for that matter support vector machines, they make very little assumptions about your data, right? So limited assumptions about data is definitely a very good way to look at it. Yes, but let me address this part a little bit more in detail. What is actually the difference? Now, classical statistics, classical inferential stats has been around for a long time. Okay, so when we typically talk about classical inferential statistics, remember, question is always the first preference. It's very question centric, right? So let me just do it this way. This is classical statistics. When we usually talk about classical statistics is usually very question centric. Okay, this might look very mundane, but the idea is in today's data-driven world, remember, the question actually forms the backseat. It takes the backseat. Data forms the center stage. All right. Now, in data science, it is more data-centric. In data science, it is more data-centric. Statistics is more question-centric. In data science, whenever you're solving data science projects, it is more question-centric, data-centric. Let me give an example for this. How is the typical hypothesis testing question addressed? Now, again, as I talk about this, remember, lot of the inferential statistics concepts you have learned will be pretty irrelevant. Some aspects are relevant, which we'll go over in the session. which aspects are relevant. But many of the classical inferential statistics, hypothesis testing concepts you have learned as you're going to the project, as you work on industry solutions in your, in your work, it will be pretty relevant, right? So when I talk about class statistics, I'm talking about classical inferential statistics, the way it was done and the way it continues to be done in many domains even today, right? So, so how is it actually working out? Let's take a minute and understand that. How is it working out? When you're first asking the question, so it's like saying, all right, so I want to basically predict what is happening, or let's say you want to basically, give me a second, guys. Just going to quickly, all right. So you want to basically predict how people in the population are going to vote, right? How is the Indian population going to vote? A classic case study for this, a very, very classic example of this will be basically predicting election outcomes, exit polls, right? So the question is absolutely clear on exactly what you want to achieve. The question is absolutely clear. Remember, first you define the question, then you collect data. So data collection happens secondary. And this aspect is very important because we are talking about, if you go back a few decades, 10 years, 15 years back, even 1 MB, 2 MB, one megapixel camera, 2 megapixel cameras were a big deal, right? So we are talking about a scenario where data was very expensive. It was very expensive to collect data. So you had to be very, very clear about the question. You had to be very, very clear about the question because collection of data was very expensive. Data was a very expensive proposition. What we have today is something very different. But as I told you, if you go back a few years, how when classical statistics, the way we approach classical stats, the question is very important. Lost voice. Okay. Hey guys, you're able to hear me, I believe. Not okay. All right, wonderful. Thanks. Okay. So in classical stats, we're talking about the question. So first you define the question, you go through the usual hypothesis testing process, and then you collect data from the sample. First, you be very clear what you want to achieve. Let's say it's a hypothesis test you want to do. I'll give a simple example here. Let's say you have your null and alternate hypothesis defined. It's a simple hypothesis test you want to perform. So first what you do is, first you go back, you define the question, you define your assumptions, what is your null, what is your alternate, and then you go back and collect sample data. Sample data comes at the very end, right? So that is how the process goes, because collection was a very expensive process. Today's world, when you talk about data science, when you talk about all the work that you have been doing in your machine learning model building phase and all that, that is data centric. Data comes first and your question actually follows next. Again, it may not go completely like that, but I'm just giving you a framework. Question only follows that. Data is there in front of you. Now from the data, you define questions, you come up with questions. It's not the other way around. Usually when you will work with any data science project, usually there'll already be a dump of data sitting in front of you. That data can come from any source. And I repeat, the source can be absolutely anything. SQL is something we are giving a little bit more stress in this particular session. I think upcoming sessions when we're going to walk through a bit of SQL. But in a real world scenario, your data can be in any kind of source. It can be in CSV files, it can be in Excel files, XML files, it can come from web data, it can be in databases. Database is a very common source of data, obviously. Data warehouses, it can even sit in Hadoop clusters or Spark clusters. Your data can even sit in a big data environment. So source can be absolutely anything. So when you typically work on a data science project, your data will already be available. It will already be lying somewhere. And from that, you start working and you define questions based on that. Whereas in classical statistics, you define the question first, then you collect data. I just wanted to be very clear on this particular approach so that everyone's on the same page on how the difference actually works out. All right, it is very dormant. It's very dormant. As I said, a lot of domains are there, Satyam, where still people use it. Many people, even in certain domains like manufacturing, processes like Six Sigma, they're still using hypothesis testing quite a lot. It's used. Many people can relate to me what I'm saying. If people are doing it, they can relate to me. Typical lot of testing, lot of classical stats techniques are still very relevant. It's not completely relevant, but the machine learning stuff that you're doing, the models that you're building, yes, the concepts are very similar. The concepts are very similar to inferential statistics, but the statistics, the way you've learned it will be very relevant. Okay, there are application areas which we'll see. How are some of those aspects actually used? How do you look at pair plots? How is the ANOVA t-test actually applied? You will see those applications, but by itself, hypothesis testing you will not be directly doing. All right, now, so I just wanted to be absolutely clear on that aspect, and that is actually very interesting because which is one of the reasons why core statisticians find it very hard to get into a machine learning job. And it's a very interesting a thing I wanted to share with you. So imagine a statistician is here. Imagine there comes a statistician, and the statistician is applying for a data science interview, right? So there comes a very classical statistician, okay, and and there comes your data science hiring manager. Okay, so very interesting actually, and the interviews are also very interesting. So there's a data science interview going on. So obviously, if it's a data science interview, so what do you expect a data science hiring manager to? Data science hiring manager will give you a bunch of data. A bunch of data is thrown at you, and the hiring manager will ask you that, hey, please tell me something about this data, right? And the interview goes somewhat like this, where the statistician says, okay, what do you want me to find? What do you want me to find? That's how it typically goes. And you can already understand the response, right? Because remember, a classical statistician will always want the question first. You cannot look at data and then define the question. That is a typical classical stats approach, right? So what do you want me to find? And the data science interview will ask you that, hey, that's why I'm hiring you for. You have to figure out what to get from the data, right? And that's how the interview goes round and round in circles, and that's one of the one of the things I that actually happens in these interviews. Okay, so just to kind of give you the understanding on, once again, what the difference actually lies between classical stats and typical data science. Okay, so just be absolutely clear with this approach, all of you. Now, coming back to our life cycle, coming back to a typical life cycle once again. So we have the problem statement here, and from the problem statement we collect data. Okay, although I'm writing like this, remember this is always an iterative process. I'm very sure you would have already learned this by now, but just to add some layers to it, it's never a waterfall model that we follow here, right? It's always an agile process, and it's a completely iterative process. So you have data, you define your problem, and after you define your problem, there'll be lots of iterations you will do with your client. There are lots of scenarios I can share you from personal experience as well, when the clients will give you some problem, and then you get to the ground level and you figure out that, hey, there is no data. There's no data available. So you have to go back. You have to constantly redefine the problem. You cannot make tall promises that saying, okay, clients will actually ask you to launch rockets to the moon, right? But you can't do that. You have to come back to earth. You have to figure out, hey, does my data exist? Is this even realistic? You cannot straight away say a no. Of course, you cannot say a no, but then you have to make a very realistic commitment only after understanding whether that data even exists. That is again a very, very core part of your data science project. Oftentimes, even from an interview perspective, what might happen is, case studies might be given to you. And as part of those case studies, we might ask you that, hey, what is the problem you have to solve? So please go back and build a machine learning model that helps me predict XYZ from this data. So even before you do that, you must question whether you even have data available for the problem. So please be absolutely clear with that particular process, all of you. Okay, so it is a very iterative process. The data collection will happen, problem will be defined, all of these things will actually happen simultaneously. Now, what is the next part? Usually whatever data you get at this level is raw, dirty data, right? Usually whatever data you see at this level is raw, dirty data. And remember, your data can come from multiple sources. Some data can come from a SQL Server file, some data can come from a database, data warehouse, CSV files, XML files, multiple sources of data could be there. And what you're basically doing at this layer is something that we call ETL. And remember, this is the layer at which you'll be working extensively with your data engineering team. What are these people called? They're typically called data engineers, right? You'll be working extensively with your data engineering team. So there's a big role divide between data scientists and data engineers. As data scientists, you're primarily involved with finding insights, building models out of your existing data. But remember, this is the layer where your raw data is already sitting somewhere, and what you're trying to do is you're trying to get it into a format which is clean, which is structured, and which is basically what you require for building machine learning models on, right? If you want to do image recognition, if you're trying to solve computer vision problems, if you want to do text mining, text analytics, NLP, natural language processing, these are unstructured sources. Text is unstructured data. Amazon reviews, Twitter feeds, Facebook posts, these are unstructured data. Your images, you take any image file, it's unstructured data. You cannot straight away put it into scikit-learn and do magic with that. You cannot. You have to convert that into a structured format. That's it. And obviously this is the layer where all your missing value treatment, your outlier analysis, all of those things will happen at this layer, right? Because remember, from your raw source, your data is coming in a dirty format, right? So you must go back and you must clean your data, all those pre-processing steps. So what is that process? What is that initial layer called? This is your pre-processing layer. And we're going to get to the technical details in a while, guys. So I'll probably just take 5 more minutes time with all of you here, and we'll come back to the technical details once again on what are the specifics to be actually done here. What are the missing values, outliers, what are the things to be done? I'm going to come back to the technicalities in a while with you. Okay. And the other name that we use is called pre-processing. Okay. Data pre-processing is what we call it. All right. Now, What next? What is the next step? Next step after you get clean structured data, and once again remember this again is a bit of an iterative process. It's not like it's not like a one-way road. It might happen that you do whatever it takes, and after a point you figure out that all right, so I just need some more data somewhere. You need some other sources, or the problem is reframed. The client comes back to you after a week and he says I want this. So this is going to be a constantly iterative process. All right. So next part will be what we call EDA. EDA stands for exploratory data analysis. All of you have spent quite a lot of time doing this, and effectively as part of EDA we are doing descriptive and diagnostic analytics. All right, so you're basically looking at the structure of your data, and effectively all you're trying to do, you're trying to find some basic insights of your data. All right, basic descriptive and diagnostic insights. So even before you build machine learning models, you must understand what your data actually contains. I think Titanic is a very common problem. I'm very sure all of you would have come across the Titanic problem, the Kaggle Titanic challenge as part of your curriculum at some way or in some way or the other. So even before you start building a machine learning model to predict survival of passengers on Titanic, you must understand the overall insights of the EDA on Titanic data, right? So at least at a basic level, you must know that, hey, you know what, females have a very high probability of survival. If you're a female, you're given more preference on lifeboats. If you're a young person, you're probably given more preference on lifeboats. Okay, you have not seen that? Okay, no problem, no problem. I'll just quickly share that link also with you, no problem. And I'll take you through a couple of case studies in my session as well, just to walk you through a couple of interesting case studies if I get some time on New York taxi prediction and another very interesting case study I've got for soccer challenge. And Kaggle challenge I'll just show you in a while. Okay, so basically you ask the question, let me just take a quick minute and just take you there. Okay, so okay, NYC New York taxi prediction. Okay, great, no problem. Okay, so all right. Sorry, I'm very sure you would have heard of Kaggle. So let me just quickly share that link with all of you. All right, just quickly opening it up, guys. And there goes the Kaggle link. Just wanted to share with you, all of you. There goes the Kaggle link. And very simple problem. And it's basically, it's an open competition. Anybody can participate. Just going to quickly send it across to all of you, okay? And I'm seeing a lot of questions coming down, but I'll probably take it up a little bit towards the end, okay? So if I'm missing out any questions, guys, anybody's questions are getting missed, so please make a note of it. And if I'm unable to answer it right now towards the Q&A section, please do ask me, okay? Don't hesitate to ask me again. All right, and Basha, I just got a hang of your question. Will we get notes for the session? Well, I mean, the sessions are recorded, Basha, so obviously I think whatever stuff I'll be doing is on the whiteboard, so pretty much you can always review the recordings, and there's nothing on the content side we are specifically talking about. And if I share some things with you, I'll definitely share with all of you in the batch as well. Okay, yeah, no worries on that. All right, so moving on, as I was talking about the Titanic problem, it's a very interesting challenge where you're trying to predict, you are basically trying to predict whether a person will survive or not based on the historical data of the passengers. It's a tragedy that happened where many people died. So you've captured all the passenger data here, which class the passenger was traveling on, what is the gender, what is the age, how many siblings and spouses the passenger had, how many parents and children the passenger had on the Titanic, the ticket number, the fare, the cabin, and finally the port of embarkation, where the customer embarked from. And based on all these parameters, you've got labeled historical data on whether the passenger survived or not. And using that information, you want to build a machine learning model that next time a new passenger has some new attributes. Let's say if I know the attributes of the new passenger, if I know the passenger is female, the class is first class, the age is young and 17 years old, can I predict that, hey, will that person survive or not with some probability? It's a typical classification problem. And of course, while you're predicting that, you can go back and you can go back and you can give your predictions there as well. Okay, so when you solve these kind of problems in a typical machine learning framework, when you're building your machine learning models, you must do your EDA, because it is only after doing EDA that you will figure out what your most important features are, right? So for example, many of the modeling that you would have learned, I think by now you got a flavor of Python already, right? And Python makes machine learning very simple. All you have to do is you call the respective classes,
For example, if you want to do logistic regression here, you please import logistic regression, logistic regression dot fit. Straight away, you might want to tune some hyperparameters. Logistic, typically we talk about the C hyperparameter. There's a regularization C hyperparameter logistic. Or if you want to use decision tree, you please straight away use a decision tree dot fit. Maybe tune some hyperparameters on max leap nodes, max depth, or you use a random forest ensemble techniques, and it works. But the most important aspect is not about the algorithms. Algorithms obviously is important, but the most important aspect is to figure out what your best features are, and that is where your EDA part will come in. So if I do my EDA properly, I will know that the gender is a very important feature. I will know that the age is a very important feature, because typically if you're young, then your probability of survival is going to be very very high. If you're a female, your probability of survival is very high. And if your class of ticket is very high, if you're basically traveling on first class, if it's first class, then once again, your probability of survival will be very high. Okay, so that is the reason why we typically prefer EDA. And let me ask you one question, because all of you have done the course. Let me ask you a question. What is that one algorithm in the classification space? Can you name that one algorithm that gives me this something called feature importance? What is that algorithm that gives me something called feature importance? Quick question for all of you. There's some algorithm that gives me feature importance. Okay, yes, PCA is there. I mean, PCA is there, of course, but there is something called feature importance we get. PCA will give you, PCA is absolutely there, I agree. But okay, feature importance we'll get from decision trees and yes, exactly, decision trees, right? So see, VIF will come in regression. That will be a different thing, variance inflation factor. So decision trees will actually give me something called feature importance. Okay, it will give me something called feature importance. Again, there are several metrics out there, but generally, okay, by the way, PCA is also there. Of course, we will be applying PCA. I'll come back to that piece as well. Okay. Hey, regression, I'm talking about a classification problem here. Okay, talking about a classification problem primarily here. All right, yeah. So your feature importance will come from your decision trees, or even your your random forest, and using that you can get a very clear sense of what your most important features actually are. So once again, when I'm working on classification problems, I usually use that feature importance to get a sense of what the most important features actually are. So it gives me a very clear indication. Of course, your EDA is important. Of course, from EDA, you'll get a sense of what your important features are. But using your feature importance, just take the entire data set, build a complete decision tree on it, and on the basis of that, you can actually get a basic idea of what your feature importance actually is. Okay. So in fact, if you go back and build a complete decision tree on the entire Titanic dataset, if you do that, you will observe that the gender feature, the class feature, and your age feature will actually have very, very high relationship with the output. Okay, the feature importance will actually come in very handy. Neha, how will EDA help us understand important features? Not directly, but let me show you some pair plots, and I think from that we'll see statistically how it actually helps us. Okay, I'll just show you that in a minute, how it actually helps us statistically. Okay. Pair plots can actually come in very handy here. How do you pick important features from decision trees? Naveen, there is something called feature importance. So when you build a decision tree model, you can actually say dt.feature importance, feature underscore importances, and it will actually print out your feature importances for you. In case you're curious how that is calculated, so decision tree internally uses what we call your your entropy. So decision tree will internally use what we call entropy to calculate your feature importances for you. Okay. And just to clarify, because I think some of you had some questions on this, just let me show this to you. I think once I show this to you, it'll be clear. Okay, bit of an important question, so I must take a minute to address that for all of you. Correlation matrix helps in EDA. Absolutely correct, Madhu. Correlation matrix does help in EDA, but that is primarily from a regression perspective. If you have a regression problem, absolutely your correlation matrix will help. But here we are talking about a classification problem. Right? In classification problem, you are trying to predict a numerical variable. So you cannot calculate Pearson's correlation coefficient between a number and a category, right? For that, what we do is we actually use ANOVA. And I'll show you how ANOVA is actually used for that problem. Okay, yeah. All right. So I'll just take a quick minute to open this up for all of you. And once again, I get some answers on ridge regression, lasso regression. Remember, they're regularized models. So of course, they're there, but specifically for feature importance, that's a slightly different thing. And obviously, PCA is an important thing. But PCA, absolutely, PCA is almost a de facto standard. We must use it. We must use PCA. And PCA will also help us select the best features using something called explain variance, right? That is an explain variance ratio. So we'll actually use a combination of both, right? And I'll show you. Let me just kind of come to the life cycle once again with all of you, how it's working out. Yes. Yes, you can do that. You can absolutely do that, Shamik. You know what? That's basically the, I mean, that's basically one of the, one of the, biggest debates that actually happened, that anyways, we are going to be doing PCA. Anyways, we're going to be, using hidden features, right? What is PCA? PCA will actually create a linear combination of hidden features for you, right? So anyways, that will give you, you're going to be combining multiple features to get a hidden feature. But the idea is, which project are you hold? Hey, Surya, just to clarify, let's come back to that part later. Project we're going to take up in the last part, 5 minutes. This is not a project session primarily. Project we're going to talk about towards the end. At a very basic level, we introduce the project today, but we're going to be talking about the project primarily from next session onwards. But I will introduce you to the project. The idea of the session is to give you some of the aspects and some of the most important things you'll be working on in the project, kind of like an overall end-to-end overview of what you have done so far. Yeah, so we'll come back to the project in a while towards the end. All right, so with PCA, one of the things about PCA will be the features that you get, A, will be hidden features. There'll be some linear combination of your existing features. So you cannot straight away look at those features and explain what those features mean. That is A. All right. Remember, the whole point of building decision tree is what? What is the whole point of building decision tree, Shamik? The whole point of building decision tree is you want to go back and make your outputs interpretable for your business, right? But PCA straight away will not help you understand your outputs. So PCA will not help you understand your output. You cannot look at a PCA feature and explain that particular hidden feature or principal component one. What is what is the meaning of principal component one? You cannot explain that to your stakeholders. Okay, you cannot explain that to your stakeholders. So PCA is largely a black box. On one hand, we are saying we want to use decision trees. And what are decision trees? One of the biggest arguments in favor of decision tree is that it is a complete white box model. You can literally look at the entire decision tree. You can print out the entire decision tree, and it just works like magic. You can see the entire decision tree. You can basically see at exactly what step, what decision is taken. So next time when you reject the loan, you know exactly why the loan is rejected, because you know exactly what decision was taken at each node. That is one of the major arguments in favor of a decision tree, right? So it is not a black box model. So now we are saying if you use a PCA with decision tree, that becomes a bit of a problem, right? So there's again a bit of a converge, a bit of a competing, line of thought on that as well. So when I talk about decision tree, so we'll typically in this space will not do PCA. Having said that, are we going to even use decision trees in production? Answer is no. There the answer is no, right? So we are not going to be using decision trees in production. You know why? Because decision tree is one of the only algorithms which suffer from very high variance and very high bias errors. Both the errors are very high in decision trees. If you build a highly overfitted decision tree, if you build a highly unconstrained overfitted decision tree, decision trees suffer from high variance errors and high bias errors. I'm very sure you come across these terms, variance errors and bias errors, right? Right, guys? So, yeah. So decision trees will suffer from very high variance errors as well as very high bias errors. Both the errors are extremely high in decision trees. Just to clarify. Okay. So from that perspective, so let me just quickly share with you. Yeah. Random forest can overcome? Absolutely yes. Absolutely yes. Random forest can overcome. Yes. So definitely, we can, random forest can absolutely overcome that. Yes. But just to clarify, okay, where is my screen gone? Oh, yes. So random forest can definitely overcome. Yes. And what I'm talking about is decision trees by itself, you will not be using. Okay. Decision trees by itself, you will never use in production. So decision trees are algorithms that suffer from high variance errors and high bias errors. Both the errors are extremely high in decision trees. And you know why? Why is my variance error high? That is very obvious, right? Variance error is high because usually the model can press to overfit badly, right? Why is bias error high? Why is bias error high? Bias error is high because it's a greedy algorithm. Because decision tree by its very nature is a greedy algorithm. And the way decision tree works is at every instant, at every iteration, it will try to figure out that feature that leads to the highest reduction in entropy. I know this is a bit confusing, because you have learned that if variance increases, bias decreases, bias variance trade-off and all that, right? But decision tree as an exception, treat it as an exception that both errors are very high in decision trees. If you build a highly unconstrained decision tree, both the errors are very high. The variance error is obviously high because you can end up with a highly overfit decision tree. The bias error is also high because it is a greedy algorithm. It's a greedy algorithm. And what do you mean by a greedy algorithm? Greedy algorithm means that at every iteration, it will choose that best feature. It will choose that feature which leads to the highest drop in entropy. And I'll give a simple example to you. Go back to the Titanic example. It will keep on selecting the gender feature. No matter what decision tree you build, no matter what train test data you take, it will always select the gender feature with the maximum feature importance without even kind of considering the other features. It is like saying the loudest person in the group will always get the most attention. The others will not get any attention because the loudest person in the group is the most important feature. So that person will always be favored. That's what the greedy algorithm disadvantage actually is. And hence the algorithm is biased towards that feature. It will always be biased towards that feature. The other features are basically as good as neglected. Which is why if you build a decision tree with hundreds of features, let's say there are 100 features and you're building a decision tree model, the decision tree model will give unusual importance to certain features. The other features will pretty much be dropped. Feature importance will actually show up as 0 for those features. And you can observe it. Like if you take a data set, your feature importance can come up to be 0 for those particular variables. Okay, makes sense? I hope I get the idea. Variance error is high. Why? Because there's overfitting. That is the obvious part, right? Because of overfitting. Okay, so please understand this part. You will not build individual decision tree models in production. Yeah. All right. Let me come back to that feature selection in a while. Let me come back to that in a while. All right. So just to go back to the original discussion once again, guys. Just to go back to the original discussion once again. So why are we doing EDA? We need to understand what our most important features actually are, which is basically called feature selection, Naveen. So what you're saying, what is feature selection? What is feature selection? Feature selection is the art of deciding what our most important features actually are, which is why we are doing EDA. In the Titanic dataset, we can do EDA. We can figure out that gender is an important feature, and then on top of that, we can build the best models on top of those features. That is feature selection. What is feature extraction? PCA will do feature extraction for you. So feature selection is one thing. Feature extraction is something else, right? So there are two things. One is feature selection. One is feature extraction. There are two aspects to the problem, right? So feature selection is one aspect, feature extraction is the other aspect. Okay, so guys, I request you some of these questions, let's just park it for a minute. So I'll just complete the story here and I'll take up some of those questions in a while, okay? Otherwise, I think we're jumping on to other things. So we'll take up some of these questions in a while and we'll take up all your questions in a while. So let me just complete my flow. If there are questions related to what I'm discussing, you can ask me. Other than that, some generic questions you can probably park. All right. So quickly, just to complete what we started out with, the problem statement comes in. You can have data from multiple sources, okay? And ETL is typically a layer that we tend to use here, okay? That is a pre-processing layer to convert your data into a clean structured format. This is absolutely mandatory for machine learning because if your data is unstructured, if you've got image data or textual data, then you cannot straight away plug it into machine learning models, okay? And on top of that, EDA is required. Some of you ask me, why is EDA required? Because using EDA, you can go back and you can figure out what your best features actually are. Okay, inside. So Vijay, just remind me about that question later on, because again, as I said, I'm going with my flow right now. In case I forget your question, just remind me that later on. What is feature selection extraction? I'll come back to that. Okay, just remind me about that question later on when I do Q&A. All right. So from that, you get insights, and your model building will only happen at this layer. Okay, your model building will happen only at this layer. This is where your machine learning models will actually start happening, and we'll come back to this part in a little bit more in a technical way, how it's going to happen. Okay, and finally, you're going to deploy your models. Remember, this entire exercise will be an iterative process. And as you will see, I'm very sure the Capstone project you guys would have worked on already. Right? It's a case study we are doing, obviously, but in the Capstone project also, in a real world case study also, as you go through an actual project, remember, all of these things will be completely iterative. You can end up building a machine learning model. You can end building a machine learning model, but at the end of building the machine learning model, you can figure out that your model is not giving the right accuracies. Your model is not giving the accuracy that the business wants. So you will have to go back to the problem statement. Maybe you have to refine the problem statement. Maybe the business wants you to do something that you cannot do. So you have to reframe the problem statement. This entire process, please remember, it will be a completely iterative process. There might be scenarios where you have to go back to your data, collect new data, redefine the problem statement, rebuild the model. There are several iterations that will happen here itself. Your hyperparameter tuning, your choice of model, maybe the ensembles, okay, maybe doing some collecting some fresh data, retraining your models. All of that will happen in this layer. Okay, and one more aspect I want to talk about little bit about is about retraining. Many people think that models are static. Remember, your models are never static. Models are never static. Sakshi, I think I addressed that. Deployment I'll talk about later. I think let's stick to the thing. I'll talk about that later. How is deployment done? So the idea is your models are never static. Your models must always change with time. Okay, your models must always change in time. So you might have trained a machine learning model on some sample data, but remember your data in the population is changing, so your models also must change with time. You must retrain your models. And I'll give you a simple example of this particular process here. A very simple way to look at this could be, let me just open this up. Okay, a simple way to look at this could be, let's say this is the population, right? This is what you're basically trying to do in all of machine learning. There goes your population. And this is why I initially started my discussion with inferential stats and machine learning, because the relevance is very striking. Okay, very striking relevance is there. So what you're basically trying to do is you're trying to build your models on the population. Whatever predictive models you're trying to build, all these models must ultimately work in your population. Okay, and this is exactly, I'm very sure you would have learned statistics as well, right? Even in statistics, whatever inference you're trying to make, whatever hypothesis you're trying to generate, that must ultimately hold in the population. So your population is dynamic, population is unknown, but all your machine learning models must ultimately run your population. I'll take a simple example of time taken to travel from A to B. Let's say Google Maps model. You go to Google Maps, you type out your destination, and it predicts the time it takes to go from A to B. Remember, somebody at the back end, somebody sitting at Google would have developed that algorithm for you. They would have developed that model for you. That model is right now working in production. How do they do it? So time taken is a very complex function. This model, there is already some function out there in the population. Now, what you are doing in all of data science and all of the machine learning models that you've built is, you are only working with a small sample of data. Go back to all the data sets that you worked on. You said you worked on New York City taxi prediction, right? That is only sample data. That doesn't take into account all the historical taxi rides that have ever happened in New York City. It only takes into account a very small fraction of taxi rides that happen in New York City, right? It's a very small sample of data. So ultimately, you are trying to predict the duration of the trip, right? I think the problem is about trip duration, predicting trip duration. So your machine learning model is trying to predict how much time it takes, the trip duration, right? Duration. You're trying to predict duration in the population, but you only have a small sample of data to work on. So you're building your models on the sample, whatever life cycle the project I showed you, whatever data science life cycle we talked about, take your data, clean your data. Remember, all of that you're doing only on your sample data. You extract a very small part of your sample from your population. You do all your data cleaning, your outliers, your EDA, everything on this small sample. You build your models on that sample. You build your model on that sample. You say duration is a function of X, Y, Z, whatever models you build. You do all of that in the sample, and then whatever models you build in the sample, you are 95% confident or X% confident that that model will also hold in the population, right? So that is basically the flow that we are looking at here, which is why the inferential stats techniques you have learned and whatever you're doing in machine learning is very, very similar. As you can see, this connection is very similar. In both cases, you're trying to build some models in the population, but the population is unknown. So what do? You take sample data. The sample should be a good representation of population. We'll see some techniques how we can prove that, how we can use some statistical tests for that. We'll see that. Okay, the sample must be a good representation of population. You clean your sample data, you do ED on your sample data, you build your models on your sample data, thinking those models will also last in production. That is, production means population. That is basically the flow. And now here is the thing. You would have deployed that model to production. You would have deployed the model to population. The model is now working population data. The problem is, a year from now, the entire landscape of New York City would have changed. The model that you built to predict trip duration, that same model cannot exist a year later, right? It's like Google Maps. The prediction that Google Maps is giving you today, maybe let's say if you're based out of Bangalore, Chennai, Mumbai, or San Francisco, Los Angeles, New York City today, then Google Maps predictions will change drastically a year after today, a year later, because the traffic would have increased. Let's say some flyover would have been constructed. So the models would have been very different. You must retrain your models in production because the population data would have changed. What you must do in that case is, now because your population data has changed, you must take a fresh sample, you must rebuild your models, and you must redeploy your models. That's the way to go about it. Okay, now what I would like to do is I would like to take a quick minute here, get a little technical, and ask you how do you actually, what are some of the statistical tests? You've all learned the statistical test, right? T-testing, ANOVA, all these things you've learned. I want to take a quick minute here at this particular phase and talk a little bit about how do you prove that a sample is a good representation of population. How do you prove that? Remember, mostly in data science, many of the statistical techniques you've learned are pretty relevant, but some aspects are relevant, which is what I'm going to get into. Okay. Now, so one of the ways you can actually do it is, and one way I always find it very helpful is to put it out in a table format. So one of the ways you can do it is, remember, in all of statistics, we're talking about two things. One is called central values. One is called central values, measure of central tendency, central values, and variance. These are the two primary things we're talking about in all of statistics. Okay. So quick things, guys, couple of quick things. Who will tell me how to prove normality of data? How do you statistically check normality of data? Have you learned these things? What is the normality? Okay, one way we can do it is to do a pair plot. We can do a pair plot, right? We can do a pair plot. You've all seen pair plots, right? SNS pair plot. Have you all seen pair plots? Okay, you've all seen pair plots. Hey, not distribution. Yeah, I mean, exactly. There are dis plots are a part of it. Pair plots. I'm talking about pair plots. SNS.pair plot. You've all seen pair plot. Wonderful. So pair plots will basically be like a pairwise scatter plot. Hey, how can you say no? Okay. Oh, hold on 1 minute. Exactly. SNS pair plot for normal distributions. Hold on. Give me a second, guys. Let me quickly bring it up. Okay. Okay. Pair plot is one of the most basic plots in data science. I'm very sure you would have seen it. Anyways, let me quickly open it up. I want to ensure everybody's on the same page. So I'm going to quickly take a minute and open up something for you. Okay. All right. I'm going to quickly, okay, you've done pair plots. That's fine. That's fine. No problem. No problem. Just going to quickly take a minute to address everybody. All right. So this is what we actually have here. And just ignore the dataset here, guys. Don't worry about the dataset right now. This is a simple file I'm just sharing with you. It's a simple, have you done this diabetes dataset by any chance? PIMA diabetes dataset by any chance? Okay. Have you seen this diabetes data? Okay, you would have seen the PIMA diabetes data. It's a very interesting data set. It talks about, it basically samples data from the PIMA Indians tribe, and women of that tribe actually have a tendency to contract diabetes. So the women of that tribe are actually studied. You've already done this. So I'm going to straight away jump to the implementation here. I'm going to straight away jump to the implementation right now. So let me quickly go back and run the initial part with all of you. And what I will also do is just do a quick pair plot for you. Okay, SNS.pair plot, and I'm going to take my okay, just become PIMA diabetes. Anyway, don't worry about that. That's a spelling mistake. It's PIMA diabetes, and I'm going to do diet kind equal to KDE. Why am I saying diet kind KDE? Because it's a kernel density estimate I want to plot. Okay, and finally, I want to also view this by hue is equal to, I want to say hue is equal to outcome. This is the way I always like to look at a classification problem. Okay, now let me see this quickly. So hold on a minute. Okay, not outcome. All right. Okay, sorry, I've dropped outcome here. Sorry, no worries. Give me a second, guys. Just gonna go back and run this here. Okay. So again, typically pair plots are very, very useful feature selection tools in a classification context. We're gonna see that's okay. That's a spelling thing. That's okay. Don't worry. That's prima. That's fine. That's okay. That's not a variable. All right. And typically these warnings can also be very, 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 very irritating. So what you can actually do is you can actually say import warnings. You can import a warnings module. Usually, if you want, you can also import a warnings module, because as you work in complex projects, these warnings can be very irritating. So import warnings, and you can say import warnings.filter warnings ignore. You can just use a simple command to ignore the warnings. Okay, you can just do that as well going forward. All right, so I will just take a quick minute, and there goes my pair plots. And what you will see right now is something very powerful. First things first, your pair plots are not normal. Your pair plots are not normal right now. As you can see, the pair plots are very bad in shape. These are all my original variables. The second aspect that I want to highlight is that my pair plots, the features are all overlapping. The distributions are overlapping. Okay. The blue and the red, they basically stand for diabetes, non-diabetes case. And right now, what you're seeing along most of the features, my distribution is overlapping. This is a very good way to select the best features. So as you can see in a classification context, this is a very hard problem. PIMA diabetes is a very hard problem. Why? Because in none of the dimensions I'm able to separate my features. This is one more visual technique that you can actually use to see whether I have good features that I can use for my model building. Okay, so you can see none of the dimensions. You can see the pregnancy dimension. I'm not seeing any good separation. I'm not seeing good separation. Glucose dimension, I'm seeing some separation, but you can see blood pressure. Blood pressure can be high for malignant case as well as for benign case. Anything. Blood pressure can be high for people who have diabetes, people who don't have diabetes. You can see this one. You can see insulin. Insulin can have the same value for people with diabetes, without diabetes. So these are not good features. Okay, you're aware of this thing, I believe, right? How to look at the overlapping distributions. You're aware of it. Okay, how to select features in such cases. In this case, it's a very hard problem. Right now, we are doing it visually. But what you can do is, in this case, you can use a t-test. And what you can do is you can compare the means of the distributions. Right? You can see if the means are very vastly spaced out. So what you can do is you can look at a t-test context, and basically what you're trying to do is you are trying to see if the means have a very separation. So the mean will actually lie here. And now you're seeing if the means are separated. If there is a significant separation between the means, t-test. So basically, you run t-test across all these dimensions and you check if your p-value is less than 5%. If your p-value is less than 5%, what does it mean? That means there is a significant separation between the means, which means that feature is very good for classification, which means that feature can segregate the diabetes and non-diabetes cases very well. Okay, so you can actually use a t-test, and if you've got multiple classes, right now we've got either diabetes, yes, no. If you've got multiple classes, then you can use ANOVA in this context. ANOVA. You can once again use ANOVA in this context if there are multiple classes. And using ANOVA, you can use a pair plot technique to actually see whether your features are significant or not. It's a very simple technique we can use to select features. Feature selection is what we call it. Feature selection. These are some basic ways I'm talking about visually, and using pair plots, how you can leverage for feature selection. Others are more advanced techniques will come back in our upcoming sessions. All right. But I hope the basic idea is clear. Let me give you one more very interesting example here. Let me give you one more. So by the way, PIMA diabetes, guys, if you have solved, you will see accuracy not going beyond 70%, 75% maximum accuracy, not more than that, right? If you use ensemble techniques, probably you can boost the performance up to 80% at the max, not beyond that, 80, 82 at the max. And the reason lies in the features. Remember, the magic always happens in data. The magic never happens in algorithms. You can do, you can use the best of the best neural networks. Okay, even in deep learning, use a CNN model, generate new features, do all the magic you want with algorithms. If your data is not good, if your features are not good, if visually only you can't find a separation, your algorithms will not do any magic. Because what are classification algorithms doing? At its very core, what are classification algorithms doing? They're simply creating a decision boundary for you, right? They are also searching for the same decision boundary. There must exist a separation. If you don't see a separation visually, your algorithms will not do any magic for you. So please be aware of that. Okay. Now, let me give you some other examples on this space, just to kind of absolutely be clear on what is feature selection. Just going to open up one more file for all of you, just to be absolutely clear on what is feature selection. I'll give it a minute, guys. So I've quickly opened up one more file here for all of you, and this is basically ANOVA chi-square. What I'm going to do is, what about using SVM with RBF kernel? Hey, hold on, SVM RBF. See, whatever you do, SVM RBF will also not do any magic. Try it out, Vaibhav. Try it out. You will still not get good accuracy. SVM RBF will not do any magic for you. If you try to make it too overfitted, then you will use your test. Your training accuracy will be very high. Testing will be very low. Okay. Now, all right. So what I wanted to show you here is a couple of other beautiful examples using ANOVA and chi-square. Okay. Okay. Let me just come back. How do you practically use ANOVA chi-square? Otherwise, those are statistical tests we have learned theoretically. What I'm trying to get at here is, how do you actually use these concepts in a more practical context in machine learning? So let me just quickly show you this one. What we are seeing right now, guys, is analysis of variance. Exactly. Yes, yes. I will share that with you. I'll share that with you, Manasa. This file I'll share with you. No worries. Yeah, I'll do that. Yeah, yeah, cool. ANOVA is new thing for you. Okay, I'm surprised. Hey, ANOVA, you guys have done, right? Yes or no? All right. No. Okay, I think that's an optional module for you, right? If you have not done, just check it up. ANOVA, I believe, is an optional module. All right, that's fine. That's fine. Even if you don't know ANOVA, I can teach you ANOVA in 2 minutes. All right. As you would, okay, that's it's it's very basic implementation level understanding you need, and we'll see that. Okay. All right, no worries. Even if you don't know, no worries. Let me just quickly talk about it. Okay. So what we have here is a simple data frame, guys, and I'll just show you monthly income DF. As a simple data frame we have got. We've got Jim along the as one of the columns, and we have got monthly income as the other column. The problem statement is very simple. We are trying to predict monthly income using Jim. Okay, so it's a regression problem. You're trying to predict the monthly income using the categorical variable called Jim. This is a simple problem statement we have got right now. Okay, now the idea is Jim a good feature? If these were two numerical variables, you can absolutely use your correlation coefficient which you have learned. Now what we are talking about is, now basically what we are talking about is, if it was a numerical variable, you can use a correlation coefficient, right? So number to number relationship, you can absolutely get with the correlation coefficient, the Korkov, R value that you have learned, right? Pearson's. Now what we are talking about is numerical to categorical or categorical to numerical. How do you quantify this relationship? How do you quantify the relationship if between a numerical and a categorical variable, or vice versa? That is basically, you can use your t-testing and your ANOVA. That's what you're getting at right now. Okay. So, so by the way, what do you think? Is there a good relationship between monthly income and Jim? If I ask you to solve a machine learning problem where you're trying to predict monthly income, is Jim a good feature? I mean, quite intuitively, what do you think? Is it a good feature? Using basic common sense, and remember, there is no substitute to domain knowledge. Domain knowledge is a must in data science, right? Domain knowledge, nothing beats domain knowledge. Okay. So not a good feature. Logically, it's not a good feature. Your Jim has nothing to do with your income, right? Your occupation has to do with it. Which city you live in has to do with it. But maybe, I don't know. I mean, if you're in a very expensive gym in a very great society, that's a different thing. If it's a very exclusive gym, that's a different story. Again, there are a lot of different dimensions to it we can think of. But generally, Jim is not a good feature, right? And you will see the magic happening once I start to visualize my data as a box and whisker plot, right? This is the visual representation of my data as a box and whisker plot. Very clearly, visually only, I'm not seeing any good relationship right now. And whatever I'm seeing from a box and whisker plot, the same information I can pretty much get from a pair plot also. You want to see that? Let me show you a pair plot as well for the same data. So what I will do right now is, I'll just go back and give you a gist of this data set here, dot head, so that you can see it parallelly along with me. And now I will do a quick pair plot for you. I'll do a quick SNS.pair plot for you. And you know what I want to visualize? I want to visualize my monthly income DF. I want to visualize a pair plot of monthly income DF. Diet kind equal to KDE. Diet kind equal to KDE. And I want to basically see Hue is equal to Hue is equal to Jim. Because Jim is the categorical variable, right? So I want to color by Jim. So let's see how this is actually working out. Let's see, and you will see this. You will see this. You will see, look at this. Look at this, how beautifully this pattern is coming out. Hey, KDE stands for kernel density estimate. KDE stands for kernel density estimate. Look at how beautifully this pattern is coming out. All of you told me that Jim is not a good feature for monthly income, and the visualization, the pair plot is actually proving this for me. You can see this is along the monthly income dimension. I'm plotting multiple, kernel density estimates, and you can see all of them are overlapping, which means all the means are overlapping, which means I cannot use the Jim, or I cannot use monthly income to predict Jim, or vice versa. So the relationship between Jim and monthly income is very low. Okay, there is not a strong relationship. There's a very weak relationship between monthly income and Jim. That is what you basically mean by overlapping pair plots. You can either draw a pair plot for this, or you can also draw a box and whisker plot to get the same understanding. And now let me show it to you in a more statistical way, because this is very hard, right? Visually, it can be very hard to interpret. What if there are borderline cases? You need a statistical metric. What is a statistical metric? There goes the ANOVA test. You can do the ANOVA test right now. We are trying to predict monthly income using Jim. You can create the ANOVA table right now. And for Jim, you look at the p-value. The p-value is extremely high. Remember, if you understand nothing about hypothesis testing, the one thing that you should keep at the back of your mind, if P is less than 5%, feature is significant, else feature is not significant. That is the one aspect you should definitely understand, or even memorize for that matter, right? So P should be less than 5%. What is 5%? 5% is the level of significance that we typically consider. As you can see, Jim, the P value is actually greater than 5%. 61% P value, it's a very high P value. So that means Jim is not a good feature. So monthly income, you're trying to predict with Jim is a bad feature. So here statistically we're able to prove that. Visually we already proved that it's a bad feature. Now statistically here comes the ANOVA results for me. Okay, so it's a very common way of understanding or mathematically representing the relationship between a numerical and a categorical variable. Okay, let's come down and let me give you one more beautiful example. This is basically National Transportation Safety Board examining the safety of compact cars, medium, mid-size cars and full-size cars. All right, so let me just show you straight away my data set here, what my data set actually looks like. All right, so this is mean pressure DF. So this is mean pressure DF. I'm going to quickly show you my data set here. Okay, so what you basically have here is car type, compact car, medium car, full size car, and the mean pressure. Basically, the car is going through a crash test. The idea is that the car is going through a crash test, and obviously, if it's a compact car, the pressure will be much more, right? So naturally, if I visualize my data, you'll see it is a very obvious relationship I'm finding, right? The compact car, the pressure is much more. The medium and full size car, the pressure is much less. Obviously, if it's a very large car, the force exerted after a crash test is much lesser, right? The same thing I can even visualize through a pair plot. The same thing I can even visualize through a pair plot. Let me just show you. So this is basically my mean pressure DF, and I'm going to go back and say Diokin KDE, which is always something I prefer. I don't like histograms. KDE is a smooth histograms. I always prefer that. Okay, and finally Q is equal to he is equal to car type. Okay, Q is equal to car type. All right, let's see this. Now you will once again see an extremely good separation of your features. You'll once again see a beautiful separation of your features. More specifically, more statistically, there's a very, very good separation of your means. A very good separation of your means. And once again, you can see that this is a very good feature. If I know the car type, I can predict the mean pressure very accurately, and even vice versa. Because naturally, if you know you're in a compact car, the mean pressure will be very high. So the relationship between the features is very strong. Visually, I can see a very strong separation between the peaks. And statistically also, you please plot out the ANOVA table. Mean pressure depends on car type. ANOVA table, car type is a very good feature. P value is less than 1%. 0.1% actually P value is coming, which is significantly less than 5%, which means this is a very good feature. Okay, I hope all of you are getting the idea on how to basically approach feature selection. This is just to give you the initial examples to all of you. Okay, and you can of course carry on with this. Remember, this is how we can use ANOVA tables. We can use ANOVA table and we can actually go back and do feature selection. Okay, and finally, one more chi-square. Chi-square will be two types of curves. That's the overlapping curve. That is correct. That will actually for that we'll have to do a separate analysis. And one more way to go about this will be you actually build different machine learning models on different clusters of data, right? That's a slightly different way to look at it. Yes, absolutely correct. You can use VIF as well. Absolutely correct. You can use VIF as well. Yes. Okay, so I wanted to give you a slightly different dimension. A slightly different dimension to this approach, because usually ANOVA chi-square is a bit of a gloomy topic, right? You learn it in statistics long back, and I think it's just relevant for you to see how to actually use this. And the way I always like to summarize this is in a very simple way. Let's say these are your outputs, and these are your inputs. If the output is numerical, if the output is categorical, and input is numerical, input is categorical, so how do we actually approach feature selection here? Numerical to numerical, we look at Pearson's correlation coefficient. Numerical, categorical, we can look at our ANOVA t-tests. Categorical, numerical, we can once again go back to ANOVA t-tests. We can do a t-test. We can very easily do a t-test. And finally, categorical, we can do chi-square. So this example could be relevant, let's say, for Titanic data. So for example, in the context of Titanic data, you're trying to compare, let's say you're trying to compare your, looking at the relationship between, let's say, your gender and let's say survived, something on that context. Okay, so that's how we can look at a relationship between two categorical variables. All right, Now let's move on. And then once again, I'll take up some of these questions in a while. Feature extraction, I'll come back to classification. Just give me a second here, guys. All right. Okay, hey, how do you compare? Oh, Gopalan, just to clarify, it is not a manual process. You can write a for each loop, and it's an ANOVA table, right? Doesn't matter if an ANOVA table will completely publish the results for you. You don't have to manually see the values. You can write a code for that, right? That's why you've done Python, right? So in Python, you can automate that process. You don't have to manually do it, not at all. Yeah. Yeah. Okay, I'll just take a quick minute here, guys. I think my just give it a quick minute here.
Hi everyone. Sanyan just got disconnected because of a few technical issues, and he's facing in a bit of rain at the moment. So he just spoke to him, and he's just joining in the next minute or two. So just hold on. We have not finished. There is still 20 minutes left, and he will even make up for the time. So we will start. We'll hang on a bit, 5 minutes longer. So sorry for the delay. In the meantime, you can just fill in the polls and give in your feedback as to how you're finding the session. And if there's anything further, you can even write it down and let me know, and I can give that feedback to the team on how we can even improve the sessions. But how have you guys been finding the session so far? Would like to hear in the comments. but just wait for a couple minutes and he will be joining.
Yeah, I think you can share. Yeah, Chinmay, I think you can share. Hello.
Welcome back.
Yeah. I'm sorry. Yeah. Hey guys, the session did not end. Okay. I think. Yeah. So I'm not sure. The session is still on, guys. I'm sorry. I think with yeah. Yeah. All right. Hold on.
I know that the session is on. I was just asking for their feedback and a lot of good
Oh, okay.
how the session is.
Oh, okay. Fine. Yeah. So yeah. Hold on. I'm sorry, guys. Actually, Indian monsoons. I'm on the receiving end of it. There's a bit of a lot of rain going on in Bangalore right now. So it's raining very bad right now. Anyone is based out of Bangalore will know this. So, anyways, just got connected back. Sorry for the delay. And all right, let's move on. All right, I'll take it up. I'll take up all your questions. Okay, guys. Yeah, exactly. It's raining very bad in Bangalore right now. All right. So let's come back. Let's come back and okay, where was I? Just give me a second here, guys.
For those asking on the poll feedback 5.
I'm sorry.
No, I was just responding to some of the queries from the.
Oh, okay, fine. Yeah.
You can go ahead.
Yeah, sure. Okay. So I was just summarizing. I think okay. Let me just share my screen with you also right now quickly. Sorry, I think just broke off for a minute. All right. There it goes. All right. So I was discussing some of the concepts around ANOVA chi-square, and I think there was a question that was raised on two-way ANOVA. See, basically, what happens in two-way ANOVA? I'll give you one context around it. I'll give you a quick context around two-way ANOVA. In two-way ANOVA, what you're doing is if you've got multiple features, it is like in one-way ANOVA, you've got a single feature, but in a more real-world scenario, what you'll be doing is you'll be working with multiple features, right? So there you'll be doing two-way ANOVA. There you'll be basically working on two-way ANOVA. And in case you're still curious, let me give you one more very interesting example on that space. Okay, because I think one of you wanted an example on quick two-way ANOVA. Let me just give you a quick example on that space as well. So I'm going to quickly open up my file. And after this, we're going to right away move to machine learning models. Okay, I'm going to spend a little bit of time on feature selection. There have been lots of questions that have come on feature extraction. I'm going to come to PCA also in a while. What are the applications of PCA? And I'm going to come to that. Talk about overfitting, underfitting, finally to machine learning models, ensemble techniques. And towards the end, let's see that. Okay, the model deployment also will come back to that in a while. Okay, all right. Okay, so just to also address the query that was raised on two-way ANOVA, let me open up my ANOVA chi-square file. Guys, I will share this file with you. No worries. You can refer to this later on as well. Okay. So please go back to all the practical datasets you have done in your sessions so far and try to apply ANOVA chi-square and see the magic you can actually do from that. Okay. So two-way ANOVA example, beautiful example I've taken. Very simple example, not a very difficult example. Okay. So basically what we are trying to see here is, I'm going to quickly run this code for you first. Okay. Couple of libraries I'll import. Go down. And what we basically have here is a simple data set, location, discount, and quantity. What is location? Location is basically the city. Let's say the city. Discount is basically the amount of discount you're offering, and quantity is basically the overall quantity you're selling. All right. Let's say this is usual supermarket data, typical supermarket data we are looking at right now. Location, which location you're from, discount, how much discount you're offering, and quantity, what is the overall quantity you're selling. So right now we're in again the typical regression problem where you're trying to predict quantity sold from using location and discount data. So first of all, building a machine learning model is very simple. You can straight away fit a machine learning regression model on this data and you can build some predictions. Now what we are getting at right now is feature selection. We're talking extensively about feature selection right now initially. So we are seeing how can we use ANOVA to do feature selection. Let's see that. So using basic common sense, we'll get some idea of what the most important features actually are. So let's build a quick Seaborn plot on this. Let's build a quick SNS pair plot on this. Let's see what kind of outputs we're actually getting. The SNS pair plot on this dataset, on this sale quantity DF dataset, sale quantity DF, SNS pair plot on sale quantity DF. Hopefully I've run this code, right? Okay, fine, yeah. Okay, hold on guys, give me a second. Pandas is not defined. Okay, let me just run this code once again, sorry. Okay, there it goes. Perfect. I'm going to quickly run this once again. Sale quantity TF and diag underscore kind equal to KDE equal to KDE. And finally, hue is equal to, you want to color by what? What do you want to color by? Let's say you want to color by location, lock, color by lock. I'm going to do dot head, okay? Because I think, yeah, I'm going to do dot head. So color by location is what we are seeing right now. So color by lock. Where is that? Sorry. Yeah. Sorry. Okay. Anyways. Discount. Okay, what you're seeing right now, guys, quickly, what you're seeing right now is a very interesting pair plot. And once again, we are trying to establish a relationship between location and the quantity. Is location a good feature? The problem statement is very simple. We are trying to predict quantity using location and discount. Which one is a better feature? Is location a good feature? Is discount a good feature? Which is a better feature right now? If you see the pair plot right now, very clearly, location is not a good feature. So quantity and the pair plot is actually overlapping. The distributions are overlapping, which means location is not a good feature to predict the basically the quantity, as you can see. So relationship between location and quantity is not good. So the simple way to interpret this will be the the relationship between location and quantity is not good. There's a very weak relationship between location and quantity. If you know the location, that does not help you predict the quantity. And I think the idea is very simple. It's like saying both are metro cities, both are tier 1 cities. You can have a big bazaar in Hyderabad, you can have a big bazaar in Bangalore. Both are tier 1 cities, metro cities, and generally the sales will not affect. Okay, but now look at the magic that happens when I take discount. If I take discount as a feature, look at the magic that actually happens here. Okay, look at this right now. Okay, sorry, discount is actually DISCO. Okay, sorry, discount is a full value. Okay, anyways, I'll do it by discount right now. And look at this right now. What happens? Discount is going to be a better feature, which is obvious. I think with domain knowledge only, we can say discount will be a good feature, right? And you can see the beautiful separation I'm actually getting. What is ANOVA technically doing? ANOVA is basically trying to evaluate how separated your means are, which is the same kind of testing we are doing in t-testing as well, right? So we are seeing how separated the means are. In other words, how separate, how spread out my peaks actually are. So we're seeing multiple peaks, and the peaks are actually not completely overlapping. There is little overlap, but there is clear separation. In other words, there is a statistically significant separation. So location and so the discount category and the quantity have a strong relationship. If I know the discount category is high, the quantities of sales will also be high. It's very obvious, right? Because if you give higher discounts, people will buy more products. And you can see how we're able to use pair plots and ANOVA testing in this context. And let me just take you back. This is basically an example of a two-way ANOVA. If I take you back, this is how we actually do it. So we can take discount, we can take lock, and we can also take a discount and lock interaction term, right? Interaction term we can create. Why interaction term? You might ask me why interaction term? Interaction term is basically very much like your polynomial features. This is like creating additional hidden features, right? So it's like saying x1 is there, x2 is there. Now you also want to create x1 into x2. It is like adding that additional interaction feature. So discount by itself is a very, very good feature. As you can see, p-value for discount is 1.05 e to the power minus 13. What is e to the power? It means 10 to the power. The p-value is very low, which means discount by itself is a significant predictor. It's a good feature. Location by itself is not a good feature because it is 10 to the power minus 1. 0.5 means 50%, not a good feature. The p-value is not less than 5% for location. And if you take discount location combination, the combination is also very close, but it's not a good feature. It's around 7%. It is higher than 5%. Okay, so this is how we can actually use an ANOVA table for feature selection. Okay, so just to kind of give you the context around this piece. Okay, I hope that answers the question on two-way ANOVA. And by the way, this is two-way ANOVA. You can do n-way ANOVA. You can have hundreds of features. You can still use the same ANOVA table, and you can look at the p-values and select what your most important features are, which is not very different. And you can already start to see this is the same ordinary least squares function you use for linear regression, right? In linear regression, you use the same concept. So that is why ANOVA regression are very, very closely related in that context. This is the same way. If you go back to the regression examples that you have learned in your sessions, in linear regression also, you would have learned pretty much the same kind of table. Go back to multiple linear regression, how you do feature selection there, you do the same way. You would have seen the similar kind of table come up there also. F statistic, DF, you would have seen that as well, right? So the T statistic will come up. So the similar way, the similarities actually show up beautifully between the two approaches, as you can see. All right, now coming back, and let's take a small digression into something else. All right, now I will do that. Do we have to convert? Of course, categorical. No, that's not required. That's not required, Sagar. Categorical to numerical. No, I mean that you will obviously do, right? Before you use machine learning SQL, naturally you will have to do that. We are talking about basic feature pre-processing. Even before you start doing all these things, you must ensure that your data is converted to numerical features, right? You must do that. Yes. All right. Let's move on. So I wanted to talk about a little bit of PCA and a couple of not PCA in theory, but PCA in practice, like a couple of interesting aspects about PCA, right? The usual thing you would have learned about PCA is dimensionality reduction, right? How many of you actually know that PCA can help us improve our signal to noise ratios? Let me ask you. PCA can actually help us improve our signal to noise ratios. How many of you have heard of that? How many of you have even heard of that? Have you heard of signal to noise ratio, PCA? Quick question, just for me to get a hang of it. Okay, heard? Okay, let me show you something really cool here. Okay, anyways, no worries. Let me show you. Okay, so so far we've been discussing about feature selection. Heard both, great. No worries, heard both. That's great. So let me show you something really cool. And again, again PCA overall the techniques and all are very different. You would have heard some basic idea about PCA and all. You would have learned a basic thing. So I'm not going to get into that aspect. I'm going to focus on some of the some of the implementation aspects of PCA. Let me come back. Let me show you. This is a simple car MPG dataset. I'm assuming all of you would have seen this dataset before, right? Now, the pair plots, I always prefer looking at pair plots because pair plots I always believe are very, very important tools of data science, right? You can see my pair plots are not good. My pair plots are not good. So diagonals are very bad. You can see very clearly I'm seeing clusters, multiple clusters along my diagonals. And you know what these clusters actually mean? What these peaks actually mean? These peaks tell you something about the clusters of data. It somehow tells you that along the cylinder dimension, you've got three types of cards. It is the cars dataset. You would have seen the empty cars dataset before as well, right? It's a simple cars dataset, which means along the cylinder dimension, you're seeing three categories of cars. Displacement dimension, you're seeing three clusters or categories of cars. Horsepower dimension, you're seeing three clusters or categories of cars. The weight dimension, you're seeing three clusters or categories of cars. Multiple clusters categories. These are basically overlapping dimensions, overlapping Gaussians, right? The simple way we look at peaks. So for example, you might be wondering, okay, how am I getting a shape like this? It basically means if you see something like this, this corresponds or translates to a shape like this. That's what it basically means, overlapping Gaussians. That means very clearly, the peaks in a pair plot give you some indication about number of clusters. And by the way, clustering and all these things you have learned, right? This is actually a visual way to help you guess how many clusters are there in your dataset. It's a very, very powerful and very, very visual way to help you guess how many clusters are there in your dataset. Next time, whenever you approach any project, do a pair plot first things first. After all the EDA, all the stuff, do a pair plot and see how many clusters you've got. And this was a question that came up before as well. Remember to always segregate your data into different clusters and build individual machine learning models on different clusters of data. Right. So for example, in this data set, I'm very clearly seeing three clusters of cars, which could mean small cars, which could mean small cars, medium cars, and large cars. What I should ideally do is I should build separate machine learning models for different types of cars. I must not combine the data set together and build one single model. Okay, you must always break your data into different clusters and you must always build different predictive models on different clusters of data. Let me give you one more very interesting example. Let's say there is a bank that is trying to build a loan classification system. Should you give loan to a person or not? Should you give loan to a person or not? Right? Remember, there are lots of different types of loans that can come up, right? There can be education loans, there can be business loans, there can be there can be credit card loans, there can be personal loans. So you cannot build one single default prediction model. You cannot club the entire data set into one single place and you cannot build one single model, right? You must not do that. You must segregate your data to different clusters, build different clusters of separate your data. So have a separate cluster for credit card loans, have a separate cluster for your personal loans, have a separate cluster for your business loans, and build different models, because once again the characteristics of your data across different clusters are different. So naturally you should build different models for different clusters of data. And once again, if you don't do that, you will once again see outliers coming up quite a lot. It's also a beautiful way to handle outliers, right? For example, let's take the same loan example. Okay, so what you have here is loan amount. Let's say you've got loan amount. So loan ID and loan amount. Simple example I'm taking. Okay, loan ID is 1. Loan amount is basically, let's say you have taken a 2 lakhs loan. Let's say loan ID is 2 and now you've taken a 5 crore loan. Loan ID is 3. I've taken a 10 lakh loan. Look at this. In this entire distribution of data, this 5 crore is an outlier. It's a very clear outlier. So what do? Do you straight away go and remove it? Do you straight away go and apply your log transforms and all that? Absolutely not. You go and plot your data as a histogram. If you go and plot your data as a histogram, the loan amount will have a highly right skewed distribution like this. So what do? This is a clear indication that you've mixed up your Gaussians, that basically business loans must be treated separately. So ideally what I will do in this scenario is that I'll go back, I will segregate this business loan data. I'll segregate this business loan data. So maybe I can segregate this business loan data here. And now what I can do is I can build a separate machine learning model for business loans. So this original distribution I had for loan amount, I have separated them out into, let's say, retail customers and business customers. And now I will get perfect Gaussians in both the distributions, as you can see. These kind of patterns will actually happen once you start working with data, right? So try to do some of these things. Next time you see outliers, always question your data and see if you've got some data from different distributions. For example, are you mixing up retail customers and wholesale customers? Are you mixing up retail customers and business customers? Are you mixing up personal loans? Because personal loans will typically not go more than 10 lakhs. And business loans can be in 50 crores. Are you mixing up personal loans and business loans? Question these kind of assumptions. That is one more reason outliers can come. So don't remove those outliers. Please build different models on them. Okay, this is one more technique, a way to actually handle your outliers. All right, now, okay, just to also come back. So this is actually a big problem in data science, right? So how do you handle this scenario? So what do you do in this scenario? One way to go about this is we can actually straight away apply a PCA. Let's see the magic that PCA does. All the eigenvectors, eigenvalue stuff you have learned, I'm not going to get into that part. The theoretical stuff and all that is aside. What it actually does is it actually creates magic like this. I'm going to once again show the pair plot to you. So PCA actually does magic like this. That's the magic that PCA does. It naturally improves the quality of your data, which is why when you do PCA, if you don't remove any dimension, remember dimension reduction only happens later. That is the final objective of PCA. That is not the primary objective of PCA. The primary objective of PCA is to improve your signal to noise ratio. That is what PCA does at its very core. You know what is the signals? The signals are basically your diagonals. The signals are your diagonals. I'm going to quickly go back and erase that part. So hold on. The signals are your diagonals. So there goes your signals. So signals are my diagonals. My signals have improved. So we're talking about the signal to noise ratio. People from electronics communication background, I'm very sure you can relate to it. So PCA is not exactly a new thing. If you go back to your radio transmitters, your radio receivers, the concept and the philosophy under which that works, so PCA is actually working behind the scenes. It's not exactly anything to do with data science. Yes, there are applications in data science. So data science, there are a lot of things we use. We use calculus also here, right? But the applications are there across all around us. It's a pretty beautiful concept actually. So signals have improved, the noise has reduced. That is what PCA is doing at its very core. What are my signals? My diagonals are my signals. My signals have improved. All my distributions have become normal right now. You can see they become perfect Gaussian distributions, and whatever clusters I had, I talk about those multiple peaks, right? Whatever clusters I had, they are coming in my most important dimensions right now. This is basically my PC1. There goes my PC1, PC2, principal component 3, principal component 4, principal component 5. PC1 is the most important principal component, the primary principal component, right? So all your important, most of the variance is captured in your primary principal components, PC1, PC2, PC3, right? So as you can see, most of the available clusters, most of whatever clusters I'm expected to see are coming in my initial principal components. So pretty amazing what it's actually doing. And what is noise? Noise is basically relationship between features. We have all heard this thing several times, that relationship between features is bad. There should ideally not be any correlation between features, and after applying PCA, the relationship between features is completely gone. So my signal has improved, diagonals have become better, my noise has reduced, the relationship between features has become almost zero, spherical balls I'm seeing along the features. So naturally the SNR has increased. And PCA, that's the reason why when you do PCA without removing any components, you take all the components. Originally here I've got 8 features. So by default, 8 principal components are created. If you take 8 principal components, by default, your model accuracies will always go up because the quality of my data is improved. So PCA will naturally improve the quality of my data. Dimension reduction will actually follow. That's the next thing. Now you can reduce your dimensions and you can get the same results, or you can even get better results. That's a side benefit. So it is basically hitting two birds with the same stone, with one stone, right? It is improving your data quality as well as it is improving, it's helping you reduce dimensions, right? So that's one aspect of PCA I wanted to talk about, which I think some people were not aware of, and hope this makes sense. Okay, all right. So, all right, let me just quickly open this up. All right, as you can see right now, this is my PCA dimension. And by the way, there's a very amazing link I wanted to share with you, very interesting link I wanted to share with all of you. So this is basically, principal component analysis. Let me quickly share this with all of you. Hey, absolutely correct, Ravi. To answer your question, we have disadvantage of PCA. You are absolutely correct, Ravi. So PCA, remember, PCA will only work on linear data. So basically, only if there is a linear correlation between features, right? Only when there is a linear correlation between features. Ravi, it's a slightly advanced question we're taking up at this stage. Maybe on the project side we can take it up. But just for your understanding, if you have non-linear relationships, you can use kernel PCA. Look up, go to scikit-learn, look up something called kernelized PCA. Kernel PCA uses the same support vector machine RBF kernels. It uses the same RBF kernel concept. There's something called kernelized PCA. Look it up. Beautiful documentation is there in scikit-learn. There's something called kernel PCA. Okay, yeah. So this is a kernel PCA, and kernel PCA can beautifully address multi-collinearity. I'll just share with all of you. You can look it up. There's some issue with the Zoom chat, I think. Give me a second. Just opening it, not opening. Anyways, okay. All right. Yeah. And finally, there's another beautiful link that talks about the PCA here. So I just want to quickly go back and just share it on setosa.io, principal component analysis. Okay. Wonderful example of PCA. And I think there's nothing close to. I've not seen a better explanation of PCA than what I presented in this blog. Beautiful explanation. Look at this one, guys. Look at this one. So this is basically just going to share this with all of you. Just going to share with all of you here, and you can look it up later. You can look this up later. Okay. So bit of a trouble to share all these links parallelly. Anyways, so if you see this right now, look at this. This is the original distribution of data. After I do PCA, this is the magic that actually happens. So always make it a pointer to PCA, all of you. So please make it a pointer to PCA. Okay. And if you do PCA, this is the magic that actually happens. Look at this. Originally, my data was like this. Okay. Again, this opens up. Hold on. Give me a second. Okay. Yeah. Originally, my data was like this. So distributions were pretty much like this. Pair plots were like this. Okay. So if you draw the pair plots along these dimensions, they will look like this. Multiple Gaussians you will find, multiple peaks you will find. And after you do PCA, the first principal component explains most of my variance. So most of my variance gets captured here. You will very clearly see the clusters coming beautifully in the first dimension. Next dimension, no clusters. So my overall molecule quality has improved significantly. My model quality overall has improved significantly. If you do the PCA here, if you look at the pair plots right now, pair plots will look like this. Okay, this is what the pair plots will look like. But after you do PCA, all my clusters will be visible on the first dimension. See this, and the other dimensions, you can see the clear separation that's happening. That's the magic that PCA will once again create for you. Beautiful block. Take a minute to go through it. The next example is even more interesting, where we have taken 17 dimensions, and explained eating style in UK. 17 dimensions are taken, and once again, you are doing PCA. PCA is a linear combination of all the dimensions, and you can see very clearly Northern Ireland is an outlier. So PCA is also an excellent technique to detect outliers, basically. So it is basically at its very core, it is helping you doing clustering, right? It is helping you reduce the dimensions, bring out the most important aspects in those dimensions, and technically helping you do clustering in a better way, right? And there is one more link I wanted to share with you, which you can go for. It will be helpful for your overall analysis. So MNIST is a wonderful, beautiful example on this on Towards Data Science blog. So Towards Data Science, I always recommend. It's a wonderful blog that you can go through as you're practicing the project and your journey of data science. It's a wonderful blog. And this actually talks about MNIST. And just to show you here, MNIST, I believe all of you would have heard of. It's a digit recognition use case. And once again, I'll just straight away come to the application here. Guys. All right. So, so we are straight away jumping onto the application. So what am I doing? I'm doing PCA n components equal to 3. I'm taking the first 3 principal components. And on that, what is the explained variance ratio? You can see the first three principal components are able to explain round about 25%, 24% of the variance overall. And now let's look at this. Let's look at this. So first, what we are doing is we are going ahead and trying to visualize our data with only two principal components. By the way, you're looking at a data set with 784 dimensions, MNIST data set. You're looking at a data set with 784 dimensions, MNIST data set. So naturally, we cannot visualize 784 dimensions. So what are we doing? We're doing PCA. We're taking the first two of the most important principal components, PC1 and PC2, and we're trying to visualize it based on that. And pretty magically, remember PC1, PC2 only takes into account 17% variance overall, maximum 17% variance. So just 17% information, I'm straight away able to get beautiful clusters. The ones are very unique. Ones are coming straight away coming here. The threes are straight away coming here. I'm getting beautiful clusters in only 2 dimensions. So you can already see the kind of magic that we can do with PCA. It is also a visualization technique. And after I take 3 dimensions, PC1, PC2, PC3, you can once again see how beautiful a clusters I'm able to create right now. So it is a technique you will use generally for doing clustering. After doing clustering, using those clusters, you can, now you know that you've got different sets of data. So basically, if you go back to the car MPG, you can clearly see that we have got small cars or medium cars, 2 different clusters of cars. On top of that, you can do your k-means and other things. Of course, that you will do. All right. And now, on each of those clusters, on the clusters of small cars, you will build your separate machine learning models. And on the clusters of large cars, you build your separate supervised learning models. So usually in a typical data science workflow, we always say you do unsupervised learning first, and unsupervised learning is very much an extension of EDA, right? Effectively, your core predictive analytics, your core machine learning is happening only as part of supervised learning. Using unsupervised learning, you're only discovering what your clusters are. All right, we've got clusters 1, 2, 3. On clusters 1, I build a support vector machine. On cluster 2, I build a bagging regressor. Cluster 3, I build a boosting model. And that's the way it actually flows. You build multiple models on different clusters of data. Okay, all right. So actually, there is something else a bit more advanced. I think, I'm not sure it is covered as part of your curriculum. This is a little advanced. I'm not going to talk about this right now. It's going to take some time. If you want to read about it, read about it. There's one more dimension reduction technique called T-SNE. It's called T stochastic neighbor encoding. And if you look at it, the results will be slightly better. But having said that, this is a primarily non-deterministic technique. So the results will not be fixed over time. You run it over multiple iterations, the results will actually change. This is called T-SNE. It's a comparison between PCA and T-SNE. As you can see, T-SNE is doing comparatively much better than PCA, even with 2 dimensions. Okay, this is a slightly more advanced technique and a little hard to explain also. So just if you're curious about it, read about it. The code is very simple. Implementation in Python is very simple. Go to this plot, pick up this code snippets, and you can run it out of the box in a Jupyter notebook as well. All right. Now, even PCA you can use kernel PCA. Bishwajit. You can use kernel PCA as well, right? That's not the problem. You can use kernel PCA as well. Yeah. All right. Now I must okay. Now this is the aspect of feature extraction. Many people actually ask me about feature extraction. Yeah, I think, actually, let's not get into that. There's some mathematics around it. If you want to learn about it, I'm happy to take it to a different session. I think T-SNE will take 2 hours. Easily, it's a hard technique. I don't want to oversimplify machine learning for you here. T-SNE is a bit of a hard technique. It's a difficult process. It's a non-deterministic technique. There's a wonderful article on T-SNE. If you want to read about it, I can share with you. But it's a bit of a hard technique. Okay. All right. Anyways, let's come back and not to say eigenvectors is not hard. Now that you've learned it, you will find PCA easy. But eigenvectors, eigenvalues, give it to anybody else who doesn't know anything about it. They'll probably take 1 day to even understand what is an eigenvector. Both are hard techniques. The mathematics is something that we should still appreciate and understand. All right. So now what I want to do is I want to take a minute and talk about this concept of feature selection, feature extraction, and how does this actually tie in with the overall process of what we call bias errors, variance errors, overfitting, underfitting. Right. Remember, when you're doing feature selection, and this is something I want you to keep in mind when you're doing your projects as well. When you're doing feature selection, whenever you're doing feature selection, you are reducing your number of features. You are reducing your features. And when you're doing feature extraction, and all of this is basically part of feature engineering, okay? And this is basically part of your pre-processing. When you're doing feature extraction, you are increasing your features. So when you increase the feature, what happens, guys? The complexity of your models will increase naturally. You've all learned these things, right? the complexity of your model will increase. So naturally, the model will demonstrate more patterns of overfitting. When you increase your number of features, if you increase it beyond the limit, if you keep adding more and more hidden features, then what will happen? The complexity of a model might go up, and that is basically where you take a stop. What are the different ways of doing feature extraction at a basic level? You can absolutely do polynomial features. The polynomial features thing that you've learned in regression, right? That is the way to add new hidden features. And of course, you can also do PCA. Okay, you can add hidden features using several other techniques as well. But these are the two techniques I wanted to briefly talk about for today. Okay, you can add new hidden features using these techniques. And how do you reduce features? You can use your feature reduction techniques. You can use your forward selection, backward elimination techniques. You would have seen that MLXtend library, right? MLXtend, you can use your forward selection, backward elimination techniques, or even you can use the techniques you have talked about, ANOVA, chi-square, and your R correlation coefficient techniques to basically reduce your features, or even your explained variance ratio technique. Okay, explained variance ratio for PCA techniques to reduce your features. So you can create hidden features using PCA, and then using the explained variance, you can, let's say, out of 100 components, you take it down to only 3 components. You take 3 of the best principal components. So effectively, on one hand, you generated new features. On the other hand, you removed 3-4 features out of it. Okay, so just be aware of this. And now, this is enough of theory. Let me show you. Unless I show you, none of this actually makes sense, right? So let me show you something really cool here. Okay, just so that you can actually connect the dots on what we are talking about. Okay, now. So, which are the good links to learn PCA? Hey, PCA, I believe you already learned, right, Naveen? I think that's part of your session, right? Okay, I believe that's part of your session. All right, hold on, guys. Just taking a, just wanted to show you something a little bit, one more thing, and I'll come back to some of the questions after this. Okay, I know there are lots of questions. I'll come back to the questions right after this. Okay, so give me a second here while I quickly open up. Okay, by the way, have you done this data set on concrete? By the way, guys, concrete data set, concrete, something on concrete. Have you done? Anything on concrete dataset, just for my understanding? Okay. Let me quickly share my screen with all of you. No. All right. PCA was okay. No problem. No problem. It's a simple dataset, not a very difficult dataset. We'll see this. Okay. We'll see this. No worries. No worries. Let's see this. Let's see this in action. Okay. Now, so what we have here is a very simple dataset called concrete.csv. I'm just going to give you a quick glimpse of this dataset here for a minute. So what I'm going to do is I'm going to give you a quick glimpse of this dataset. So demo.head. We'll load this in for a minute here. There goes my dataset. Can all of you take a quick minute? I know it's a little late, guys, and I think I'll take 15 more minutes with all of you. Not more than that, I promise. So I'm going to take some time for questions also at the end. So yeah, this is a simple data set: cement, slag, ash, water, superplastic, fine aggregate strength. And ultimately, using all these different parameters, you're trying to predict the strength of cement. What is the use case of this data set? We're trying to predict, what is the machine learning use case here? You're trying to predict the strength of cement. What is the strength of cement we are getting? Using all the different parameters, it's a regression problem. It's a classic regression problem. Now, the couple of aspects I wanted to talk about that you must take care when you're working on a real world project. Okay, and where does PCA fit in? Where does your polynomial features fit in? How is overfitting, underfitting happening? Just wanted to quickly brief you on these concepts before we move on. All right. So first things first. If you're looking at a data set like this, so how should you approach it? Of course, you should do your initial, correlation coefficient analysis. All these things you will do, right? Now, if you look at this data set right now, out of the box, if you see, I'll do a quick demo.core for all of you here. I'll do a quick demo.core for all of you here, and sns.heatmap. If I do a quick sns.heatmap, you will see that there is hardly any correlation between features. This is a very interesting observation that I wanted to give you. Maybe a bit of an assignment also you can take back after the session, and you can work out on this problem from your end as well. You will see this right now. The correlation between features is almost non-existent. There is no relationship between features, hardly very, very weak relationship between features. If I do SNS.heatmap, take a quick, okay, hold on. I've not imported matplotlib. Sorry, my mistake. Okay, hold on. From matplotlib, import pyplot as PLT. Sorry, as PLT. All right. So there it goes. As you can see, there is very, very weak correlation between features. And I think it's a little hard to see the numbers. Let me just show the numbers to you directly straight away. I think that will be a little easier. If I just quickly show you the numbers right now, you will see there's hardly any relationship between features. Demo.core, you can see very, very weak correlation. Very, very weak correlation. There is hardly any correlation between features. Now, on this kind of a data set, you try applying PCA, your model will not improve. I repeat, you try applying PCA on this data, you try to build a regression model, even a multiple linear regression model on this data, your PCA will not improve the results. You try it out. Actually, your PCA results will be very similar. Your PCA results will be very similar. This is the kind of use case where, you know what I do? First, I do polynomial features. So PCA on this data will be very, very poor, because PCA will only work if there is a good, strong linear correlation between features. If you don't have a linear relationship, if there are non-linear relationships, and how do you discover non-linear relationships? That is, of course, through your pair plots. Of course, you can do a pair plot. Of course, you can do a pair plot, and you can actually see visually if you're able to observe any non-linear relations. So all those things you can do. Of course, all those things you can do. You can visually observe if there are non-linear relationships. And if you observe non-linear relationships, then you can absolutely do your kernel PC and all those things can apply. All that is there. But then your PCA out of the box will not be like a magic wand for you. So please be aware of that. If your data set does not have a linear relationship, your PCA will not work. Let me show you here. And these are a couple of aspects which I want all of you to take care of as you're working on your projects as well. As you can see, I'm not seeing any clear trends. The only clear trend I'm seeing is basically between cement and strength. Otherwise, it's pretty much like, I'm not exactly seeing any non-linear relationship. These things are of immense concern to me. These things are very concerning to me. These are the kind of patterns that I want all of you to actually observe while you're working on your project as well, right? You can see superplastic, 0 values are coming, 0 values for ash, 0 values for slag. These are of immense concern. This could mean missing values or whatever. We need to analyze, especially these kind of straight line patterns are very concerning usually. So we need to observe these things in detail, why they are happening. And once again, you will observe that this is not exactly a very good data set. Lots of noise is there. So there's a huge scope. There's a huge scope for improvement you've got in this data set here. Okay. So DiKind equal to KD. If I do, I will see multiple overlapping distributions, multiple peaks. And overall, my data is extremely of poor quality. So there's a huge scope. I can improve the quality of my data here. Okay. And let's see what is the magic I can actually create here. So what I've actually done here is, I think the time is a bit limited. So what I will do is, first of all, I've actually added these layers. Okay. And what is the basic workflow we are following here, guys? Just try to walk you through it. What is the workflow we are following? So first, I'm creating polynomial feature with degree 1. Okay. So let me build a simple polynomial model first. Let me build a simple polynomial model. Let me show you how I'm actually improving the results of PCA. Okay, this is a simple polynomial model I'm creating right now. And this simple polynomial model with degree 1 is giving me 61% accuracy. Okay, you can see straight away out of the box, degree 1 polynomial. Degree 1 means what? It's just like a multiple linear regression model. Okay, very poor accuracy I'm getting. Extremely poor accuracy. You all learn polynomial features, so it's not new for you. Let me increase my degree. If I increase my degree to 2, what happens? Now we are basically creating high power degree. Highest power is basically 2, x1 square, x2 square, and x1 into x2. What is the meaning of this? It means if I have 2 features, it means if I've got 2 features, x1 and x2, I will end up creating x1 square, x2 square, and x1 into x2. I end up creating 3 additional features. Actually, in sklearn, it also adds an additional bias term called 1. And you can ignore that as well. You can ignore that term as well if you want. Okay, so that's basically how we create new features. And if I do that, let me show the magic that actually happens. I will take degree 2 for you. I'll take degree 2 and see my accuracies have actually improved. And I'll take degree 3 for you now. I'll take degree 3 for you now and see my accuracies have improved further and all the way to 84%. This is the magic that actually happens if you keep adding new hidden features. Remember, polynomial features are very much like black boxes. Originally, my dataset had something called cement. What is the meaning of cement square? Nobody knows. You cannot explain that to business, but yet it just works. Which is why in data science we say correlation does not imply causation. There is a huge correlation that exists, but causation is very hard to establish. Ash square, cement square, what is slag into ash into water square? Nobody knows, but you know what? It just works. The correlations add up beautifully. Okay, let me show you something a little bit more interesting. Now we have created a polynomial regression model with degree 3, or let's say with degree 2. And what I'm going to do is, there are not many features we have got, right? Or let me say degree 3 only. Degree 3, how many features we have got? Let's see, degree 3 most likely we'll get. I'm going to quickly do a polyxtrain dot shape. Let's see how many dimensions we have got. We got 165 dimensions. Okay, so 165 will be slightly hard to create a pair plot on. So what I will do is, let me just do a simple. Okay, let me take degree 2 itself. And degree 2, we have got only 45 dimensions. So what I'm going to do is, I'm going to create a simple pair plot on this. Okay, this is my polyxtrain. So polyxtrain is a NumPy array. So what I can do is I can convert to a data frame. I can convert to a simple data frame. And on this, I can create a simple pair plot. SNS.pair plot of this polyxtrain and diakind equal to KDE. This part is obvious, right? Diakind equal to KDE. Let's see what happens right now. Oh, hey, I'm sorry. I wanted actually, I wanted a correlation matrix, not a pair plot, sorry. So I'll do a correlation matrix dot call, and this will be wrapped around SNS dot heap. Okay, I'm going to quickly just go ahead and interrupt the kernel because this might take forever to run. Hold on. I mean, pair plots are computer intensive. There was one of you who asked me a question. There is nothing you can do about it. Okay, you have to wait, and that's one of the other things around data science, right? You have to wait it out. There are 45 features. So what I want to show you right now is, originally with my original dimensions, there was not much correlation. There was not much linear relationship. So there was not much correlation between features. But now when I convert them to principal polynomial features, degree 2 terms, I got 45 features. Between some of those features, I will definitely have strong correlations. That is what I wanted to visually show you. Okay, it will take a little bit of time to render. So while it renders, I'm going to quickly go back and show you some of the other aspects. It will take a minute to render. And naturally, you can see what the magic that's happening here. So naturally, my model performance actually improved here. Okay, give me a second, guys. I've interrupted the kernel. I think I've not restarted it. Sorry, give me a second. And okay, as it executes, what is the next aspect? The next aspect is, once you're able to do this, now after doing polynomial feature, you can do a PCA. Okay, and remember, throughout this whole process, scaling is also a must. As you're working on your data science projects, you must also do scaling. And the order is also very important, in what order you actually perform it. So please be aware of those aspects as well, in what order you perform these operations. And I think as we work closely together in the projects, we're going to get some more clarity on some of these more advanced stuff. We're going to talk about those things as well, what order you perform. But this is just to give you the initial intuition and the understanding on how to go about some of these things. All right, sorry. Okay, Matplotlib is not imported. Sorry. Okay, import pyplot stlt. And you can see the beautiful patterns that are coming up. Look at these patterns. Look at these wonderful patterns. Look at these light patterns. Okay. Initially, there was hardly any relationship between my features, but look at the beautiful patterns coming up right now. Look at these very, very light patterns. There's a very strong relationship between these features, and I'm able to visually see it. Okay. Actually, 2 took very little time. I think 3 should also take not take much time. Let me just try it out. And while it executes, I'll also go back and kind of just show you. So I'll see a very nice relationship. Look at this. This is basically with 165 features. And look at this. Initially, with my original features, I had no relationships. Now with my new hidden features, you're able to find very strong relationships coming up in pockets. Look at this light shades. The light shades, look at these clusters. I'm able to see very strong correlation between the features here. And it is exactly in these places, that PCA will actually work magic. So PCA will actually work beautifully after polynomial features. So try applying PCA after doing polynomial features. It will work like magic. That is exactly what I've done in the last part of my code, which I wanted to share with you finally. So hope all of you got the idea, right? So now I can very much do PCA on. Now here correlation coefficient is very high between features. This is what PCA can leverage, and PCA will give me very good outputs right now. So now the next part of the code, I've actually gone ahead and done PCA. There's several things I'm doing here. So first I'm doing polytransform, polynomial feature, then standard scaling, and finally do PCA. Okay, and just wanted to show you the results of my model. So this is the PCA explain variance, not required. This is a different thing. Just ignore it, all of you. I wanted to show you without PCA and with PCA results, and the results will be actually very striking. With PCA, naturally, it will be always better. It is better in this context. If you don't do if you don't do polynomial features, remember PCA will not give you good results. You must do PCA on polynomial features, because, and you can see the results I'm getting right now. Okay, it's slightly better, and it's happening because I've restricted my n components. I will just remove the limits right now. If I don't give n components, what will happen? By default, all the features will actually come. And you can once again see. You can once again see. I remove the n components, and what will happen? Let's see. And I think these kind of hacking skills are very important, guys. I think this is only going to come once you actually work with real data. And that's exactly the kind of practice we want you to get. So it's one thing to look at it from a theoretical perspective, but once you actually see the code, this is like hackathons, right? It's like participating in hackathons where all the theory, all the concepts you've learned, they are very relevant, but at the end of the day, you have to get the job done, right? I don't care about how you do it, what you do, what techniques you use. At the end of the day, you have to get the job done, right? So that's the way to look at it. It's almost like a hackathon, right? So people participate in hackathons, people working in Kaggle platforms, they're like, all right, we just need to get the highest accuracy. How we do it, what we do, I don't care. Okay. Anyways, so as you can see, with PCA, we're able to do magic with this data. Without PCA, models are getting poor accuracy. So naturally, beyond the point, if you go beyond the point, let's say with polynomial degree, if I take 4, will it be good? Actually not. So this is basically where the models start to overfit. If you create too many hidden features, feature extraction is great. If you start with degree 1, it's a very basic model. It's an underfit model. Degree 2, slightly better. Degree 3, even better. Degree 4, my model will badly overfit. My model will badly overfit. R squared training will be very high. R squared testing will come in negative. That is a sign of a very, very poor model. And this is exactly the kind of thing that you actually look out for when you're building models. Okay. Remember, I repeat, there is no magic wand technique that tells you what the best hyperparameter should be. In machine learning, hyperparameter tuning is still a very, very important aspect. Something that we'll talk about in our upcoming sessions also as we get deeper into the code and all those things, right? But then please be aware of the hyperparameters as you're working on these algorithms. There is no magic wand. You have to iterate, not randomly, of course, not through brute force completely, but you get a sense of it. After a couple of iterations, you get a sense of it. Okay, beyond this point, my training is going to go up. My testing is not going up any further. So that's the point at which you stop. And you get a sense of it. After you work with enough data, you get a sense of it. Okay, that is the point at which you cross the threshold zone. You stop there. All right. So this is going to take some time, guys. So I think degree 4 and 200 iterations. You might be wondering this piece of code. So I'm actually doing multiple random train test splits. Okay. I think by now you would have learned only a single way of doing train test split, right? But remember, a good model is that model that performs equally well on training and testing data, right? Across multiple iterations of training and testing data. So this is a very simple example I wanted to show you. A very simple example I wanted to show you. In a more real world scenario, the same thing we can do with a cross validation as well, right? So you want to iterate and execute that model, evaluate that model across multiple instances of training data and multiple instances of testing data. But in this case, we're just doing it through random train test split, okay? So just taking I range, random state, and creating different training folds, different testing sets, and basically building the same model over different training and different testing. And finally, calculating the average training and the average testing accuracy. The code is very simple. It's not very tough to actually get a sense of it, what we are doing. Okay, so that's basically what we are doing as part of the code, just to clarify. Okay, anyways, I must interrupt the kernel right now. I think it's going to take, okay, I think it's run. All right, great, cool. Let me show you. That's what overfitting looks like. Look at this. Look at this. Very, very bad performance. So turns out degree equal to 4. I don't care whether you do PCA, not do PCA. I don't care. Doesn't matter. Both cases, training is very high, testing is coming in negative. That's a clear sign you cannot go to degree 4. And that's the point where you stop. You try degree 5, degree 6, nothing will happen. You must stop in degree 3. Okay. And now one more aspect I wanted to show you, n components. Look at this one. Look at this parameter. I wanted to show this to you. N components equal to 1. Look at what will happen here. Look at what will happen here. Degree is 3, but n components is now 1. You're taking only the first principal component. Your testing accuracy and your training accuracy will be extremely bad. And I'm very sure you can understand why. I'm very sure you can understand why. Because you're taking only the first principal component. Look at this one. Look at this one. Without PCA like this, with PCA, horrible. I mean, it's even worse than horrible, right? You take 5 principal components, even then, not great. Not great. And you can understand why. Because the top 5 principal components, there are total 165 odd features we have got. The top 5 principal components are only able to hardly explain 5%, 10% of variance. So there's no magic you can do with only 5 principal components. That is the other hyperparameter you must use.
Okay, so PCA is great, but when you use PCA for dimension reduction, be very clear that how many dimensions you're finally taking. And you can see once again, although I've applied PCA, although I've reduced my dimensions, even then, after applying PCA, I'm actually getting a lesser R squared value. So you must be very clear. So first you create a baseline model without PCA, and then you apply PCA. And actually, whatever number of dimensions you take, there's no hard and fast rule that 80% explain variance and all that, 85% explain variance. Go to some blogs, they'll tell you 30. That's not there. You build a baseline model, you see what you're getting without PCA. Whatever you do with PCA must give you better results. Must give you better results, and that's the iteration you must do. Okay, so let me take it back to 50. I think at 50, I'm reasonably sure I'm going to get a better performance here. Let's see. Around about 85 to 90% variance, you'll start to get good accuracies. That is something that we have generally observed, but that doesn't mean that will hold true for all my datasets. Okay. So let me quickly run this. Now I'm taking the top 50 principal components, and hopefully at this range, we're going to get a better testing score compared to the, without PCA. And yes, I think I'm breaching without PCA here. So with PCA is coming as 80.79. And over this, naturally, if I go and improve my principal components, if I make it 100 principal components, naturally, the more features I add, feature extraction, the more features I add, I end up building a powerful model. Okay, so that's the difference I wanted to highlight. Very important, feature selection. So when you do feature selection, this is basically when you say number of features is 1, you are technically doing feature selection. By PCA, you are increasing your features, and now when you set n components, when you take your top 1 feature, when you take your top 1 dimension, that is basically when you're doing dimension reduction, you're reducing a number of features, so you're going towards underfitting. So please be aware of that. Please be aware of the concepts when you do what. And just to kind of neatly summarize this particular thing in a figure, just so that all of you are absolutely clear where we are coming from, just to neatly summarize this thing in a figure. I'm very sure you've seen this before as well. Not the first time you're seeing this. This is basically what we are looking at, error. And there goes your model complexity. And there goes your test error. There goes your train error. As the complexity of the model increases, model complexity increase means features increases, and features increase means basically we're talking about overfitting zone here. All right, there goes overfit zone here, and you have underfit zone here. And usually all your machine learning models, whatever machine learning models you build, by the way, what is error? Error can be thought of as 1 minus R squared for regression. It can be thought of as 1 minus accuracy or precision recall for classification. I usually for classification, we also see 1 minus AUC, area under the curve. So either way, the multiple metrics you can actually define for error. How do you define error, right? We can compare our testing error, our training error, and basically there comes a good fit zone, which is so elusive and is so hard to find. And yet that's a search that we are kind of trying to figure out in all of machine learning. So where is that good fit zone? What is that point at which I can say my model is just about in the good fit zone? It's neither too overfit nor too underfit. What are the hyperparameters? What is the best algorithm which is able to take me in that zone where the model is neither too overfit nor too underfit? Remember, overfitting means high variance, less bias. High variance, less bias. Underfitting means high bias, low variance. And finally, all of the feature selection stuff that we talked about, feature selection will take me towards underfitting. So this is basically doing feature selection. If you do too much feature selection, you will end up in underfitting zone. And if you do too much feature extraction, that will end up in overfitting zone. Feature extraction means adding hidden features. If you do too much PCA, if you do too much of polynomial features, you will end up in overfitting zone, right? So that's basically the crux of where we are, okay? So all the techniques you have learned, remember at the end of the day, you must compare your models along this model accuracy curve, and you should be able to figure out the best model, okay, based on this. In a more real world scenario, we will always use ensembles in production. In a more real world scenario, we'll typically prefer using ensembles in production. Why do we prefer using ensembles? Because ensemble models are those models which will try to balance out your bias and variance. There's some mathematics behind it, which I'm very sure you would have studied about. So going forward, even in your projects, whenever you work on your projects, of course, you should build your baseline models. The approach should always be to start out with basic models. We'll start off with a linear regression. We'll start with polynomial features. We'll start off with a logistic addition, freeze, or support vector machine. But finally, when you deploy your models, when you build your final models, so please build ensembles. So ensembles can be of 2 types, right? So either you use a bagging model, So ensembles can be in the bagging context, When do you use bagging models? When you want to reduce your variance errors. That is, you want to reduce overfitting. If it's a very powerful model, you want to reduce the overfitting, use bagging models, and you can use a boosting model typically if you want to reduce underfitting or if you want to basically reduce bias errors. Okay, so these are two primary ways of doing ensembling, right? And what is this random forest? A random forest is a special case of bagging, right? So whenever you're building, ensemble techniques, and basically there's something else called stacking. Stacking is kind of where the algorithm is different and the data remains the same. Right? Something else called stacking is also there. Okay, whenever you're building your models in production and even as part of the project, so please try to use your ensemble models going forward. Right? Use your bagging techniques, your boosting techniques, and remember, as you already know, that all these algorithms, even all your classification algorithms for that matter, your decision trees, your random forest, your support vector machines, your KNN, they come in, they come in a regression variant as well. So you pretty much have a k-neighbors regressor, you have a support vector regressor, you have a decision tree regressor, DTR, you have a random forest regressor, RFR. So all these classification algorithms, they also have their regression counterparts. You have a bagging regressor and you also have a boosting regressor, add boost regressor and gradient boost regressor. Okay, there are regression counterparts available for all these algorithms, with the exception of logistic and Naive-Bayes. Logistic regression and Naive-Bayes are the only classification algorithms where regression are not available. Otherwise, you can use them interchangeably in both cases. Okay, so just be aware of that. So as you're working in the project will be, it will be based on a credit data set. It is a very interesting project, and we'll be focusing on, as part of the project, we'll be focusing on several dimensions. The initial dimension will be very basic. The first session we'll be having is not going to be very difficult. It will be on SQL primarily, where we focus on the data collection aspects, where once again, data will be in different sources, data 1, data 2, data 3, multiple sources of data will be there. And these are basically going to be data sets in a tabular format, in a simple CSV format. You'll be required to use SQL, write SQL queries to get your data in one place, right? We'll get some good amount of hands-on with SQL in the initial part of our project, right? And then from there onwards, we're going to be getting to core machine learning, right? All the workflow we have talked about today, we're going to be getting into that. So first things first, it's going to be a credit default data set. Very interesting case study on credit default. We're going to be using live credit bureau data, and we're going to be doing some credit default analysis. Very interesting. Lots of missing value use cases we'll have, lots of outlier use cases we'll have, and we'll finally build some amazing models on this data set. But initial part of the session, at least for the next 1 week that we have, we're going to be focusing on taking data from all these different individual tables, like customer data, the credit score data, and from that we're going to be learning and getting some good practice on SQL queries. Because usually, whether be it you're preparing for some interviews or for your so usually these kind of questions get asked, and especially people who are looking at from an interview perspective, SQL is still a very, very common way to import your data, right? Because most of your data in real world scenario, it will be in databases, you will be working with data warehouses, you will be working with Hadoop setups, Hive and all those, and with the syntax and the queries that you use in all these scenarios is very similar to SQL. It's a very, very common language and to be very comfortable with. Okay, we're going to be getting some good practice on that. Primarily, this is called a data extraction layer. That is what we're going to be focusing on initial part. Okay, and then from there onwards, from the session 2 onwards, we're going to be getting to EDA, doing some plotting, understanding our data, that hey, you know what, let's say people from northern region are, let's say, more likely to default, whatever, those kind of patterns we'll actually try to find. Interesting patterns, let's say marriage status or single status, some kind of what has your credit score got to do with your loan repayments and all those things. All those EDA stuff we'll see. And after that, from session 3, 4, 5 onwards, we're going to come to the machine learning modeling stuff. Okay, and I repeat, as you're working on these things, so please be aware on using ensemble techniques. The individual models you will never deploy to production. You will never deploy individual models to production. Use ensembles. Ensembles help you reduce your bias and variance errors both, right? So that's the way we'll actually go about it. Finally, there were lots of questions that actually came up on deployment. Obviously, deployment we're not going to be doing live as part of the project, but be aware of it. There's a very nice article I can share with you, which you can read, as if in your overall, in your overall analysis, you can just go back and just look at it. I'll just quickly share this particular thing with you. The deployment is not a very difficult thing. Just going to quickly go back and share this with you, how to deploy a machine learning model in Python. Okay, so basically all the models that you actually built, there's a small blog that I wanted to just go through, run you through. Okay, I have a sample code, but I think we are a little out of time, so I'll just take some time for questions. And other than that, This is a simple process. Remember, once again, I repeat, as part of a core data science project, you may not be involved in a big way in this particular part, but the initial part you should be aware of, right? A lot of different things like Flask and all you use in this particular process. All right, anyways, initial part is very simple. What are we doing? We're building a simple regression model. All this while we work with simple Jupyter notebooks, right? We work with simple Jupyter notebooks. So this is a simple regression model that we're building. As you can see, train test plate linear regression.fit. And now what we do is we actually use a pickle file. We actually use something called a pickle file. What is a pickle file? A pickle file is just a simple, it's just like a simple file format, just like a doc file or an Excel file, just like a simple file format. Turns out it's a serialized file format in Python. It's very, very specialized for Python. Okay, so pickle is used to serialize and deserialize the Python object structure. Okay, so what is serializing? It means the Python object, that means the Python model object. Regression is a Python model object, right? You are converting that Python model object into a byte stream. You can basically convert it to a byte stream. It's a little technical, so just to keep things simple, the pickle is just like a file format. It's a serialized file format. So what you can do is you can build your regression model, you can fit your regression model here, and now you can dump that regressor object into a pickle file in your path. It's basically in a hard disk. Now what you can do is, this is basically what you do the client side. So from my system, what I do is I do all this modeling today. I did the concrete modeling, I did the PCA modeling for you today. And now what I do is I save all these models. And now what I will do is that pickle file that I've created, I will email it to all of you. Let's say as an example, okay, I will email it to all of you. Now what you can do is you can go back to your Jupyter notebook and you can simply do pickle.load. You can open that particular pickle file. You don't have to do anything else. Just open up a new notebook. Just say pickle.load, open up that new pickle file, that pickle file I emailed you, and straight away you can say model.predict. So pickle file actually has the model saved in it. And this is basically how a simple deployment process actually works in Python at the most basic level. Create a pickle file and send that pickle file across to the client's end. And in the client's end, you are simply running a model.predict code. Now, how is it actually happening behind the scenes? Now, there are several other ways you can implement it through a web service. Now, technically, what actually happens is, if you think about this particular, this particular piece, technically, what happens is, this is your regression object, right? So there goes your pickle file, which we created right now. There goes your pickle file. This pickle file will typically be sitting in some box. That's the pickle file which I shared with you, right? This is the regressor.pickle file. So the idea once again is what is the idea? Idea is I created the pickle file. This is Cyan. This is the model I built today. I created the pickle file, dumped it, and sent it to all of you. The pickle file is now in a box. I've saved it in a box, .pickle. Now remember, there are applications in the outside world that want to interact with this particular pickle file. What is this application? These are websites like your, like your Magic Bricks, like Glassdoor. You go to Glassdoor and you enter your experience and salary prediction comes out. What is the expected salary you can earn? These are applications. These are web applications in the outside world. They want to interact. They want to interact with my pickle file. So they want to basically use my pickle file for making predictions. So how does it happen? So one of the ways we can actually do it, because right now it's a very local process. So what you can actually do is, and this is basically where your role as data scientist ends. This is where your role as data scientist ends. This is basically where you give it to your application development team, your web apps team, and it is basically, this is the time when they take over, usually, right? Because this basically gets into a lot of other aspects, IT infrastructure, all those things come in. And usually you are not involved in this process. So now, just to kind of talk about it, what you do is you create a web service. So this pickle file that you have created, you create a web service. So it's just like a HTTP call, right? So when you click on google.com in your browser, what happens? You send a HTTP request and a response comes back. It's a request response mechanism, basically. The same way your applications, the outside applications can interact with your pickle file. They can actually make a web service call. So you can expose that particular thing as a web service. And now applications on the outside world can make web service calls, just like HTTP calls, and they can interact with that application. So the idea is very simple. It is like the application calling. This is basically like calling that model object, and the model object doing .predict and returning the results. The regressor.pickle is basically doing predict. Is basically doing predict and is returning the result back. That's the basic way it's working out. This layer, whatever layer I've done here for you, this layer is actually implemented using several web frameworks. And there are several popular web frameworks out there called Flask, Django. And as I said, this is the part where your role as a Python developer, your data science developer ends. This is core web development. Okay.
Flask and Django are very popular web frameworks available using which you can implement this thing. And if you're still curious how to do it, you can go back to this link. And the next part is going to be very, very technical. This has nothing to do with machine learning, where you create a server.py file and you can write some code here. Okay, server code. And you can see how we have done it. Request py file you can create. And that's how we can actually just create a simple implementation locally. All right, simple salary predictor you can create. All right, this is just a simple way how you can deploy your machine learning models in production. Having said that, let me clarify, in a real world scenario, you might be working on different cloud platforms like AWS, you might be working on Azure, Google Cloud, IBM. So whatever cloud platform you work on, different cloud platforms, different cloud vendors will have their own proprietary ways of deployment. So just be mindful of that. So whatever techniques we are seeing right now, this is the Python way of doing it, but deployment mechanisms might change and will be different across different platforms. If you're building machine learning models in Azure Machine Learning Studio, or if you're using Google Cloud Platform, or if you're using AWS SageMaker, they will have their own proprietary ways of deployment. So there are lots of different ways to deploy. This is just one of the more popular ways which I wanted to show you. All right. Okay. So I think we can break for the session today. I can take up a few questions right now. We kind of went through the overall process, just recap the process for you and some of the important aspects to look at. So please use your ANOVA t-test effectively. It's a module that we usually learn in a theoretical manner, but wanted to take some time to give you some practical aspects on how ANOVA t-test can be used for feature selection and what is feature extraction. Remember the signal to noise ratio part, very important. PCA will improve the overall quality of your models. And whenever you're evaluating, whenever you're doing PCA, relationship between features should be there. So create polynomial features, do your scaling effectively, and only then apply PCA. And PCA, little bit more advanced kind of PCA will be kernelized PCA, which is going to work very similar to your SVM models. And another very important takeaway is when you're implementing machine learning models in production, please implement ensemble models, right? Absolutely, you should create your baseline models. Start with simple models. This is also a point that came up some time back. So you should absolutely start with basic baseline models. But then when you implement your models in production, when you productionize your models, they must be ensembles, because ensembles are the only models that will help you reduce bias and variance errors both. Bagging will reduce variance errors, boosting will reduce bias errors, and now I'll tell you one another very interesting. There's something called boosted random forest, right? Random forest will anyways reduce your variance errors, and boosted random forest can reduce your bias errors. Pretty powerful algorithm, right? But obviously, if you go to Kaggle competition and all, another very popular algorithm that gets used quite a lot is XGBoost. Very popular. So you can pretty much use it is kind of algorithms, and once again, as I said, obviously we'll be doing a case study in a detailed way, but that doesn't stop you from going back and practicing some of these things in your Kaggle environment as well, right? You go back and take some sample sets and keep working on that. Okay, maybe I'll take some time for questions, guys. I know it's a little late, but people who want to drop out, maybe take 5 minutes for questions. Model is in production, giving some accuracy, and after some time later, the accuracy decreased. So, okay. So Ganesh, that's a monitoring part that you anyways have to do. Remember, if it's a one-off case, I will not be too worried. If it's a continuous pattern, so very important that in data science, it's not enough for me to develop a solution and for me to just deploy the solution to the client and say job over. There's an entire team out there that will be monitoring your performance, right? If it's a one-off case, I will not be worried. But if it's a continuous pattern, I will be worried, which means model retraining is required, right? Exactly. Model calibration, recalibration, all that is the same jargon, Sir Rishi. It's basically, model hyperparameter tuning and model retraining. It's all the same jargons and the same stuff that people talk about. Yeah. Yeah. I see use case of Naive-Bayes, Gaurav. Naive-Bayes is typically very useful in the case of NLP, natural language processing, text mining. Whenever you do that part, NLP Naive-Bayes is almost a de facto standard. Why is Naive-Bayes called naive? Because it makes a naive assumption that your features are independent. NLP, you will be using Naive-Bayes as a default, and usually the multinomial version of Naive-Bayes. See, industry projects, I prefer Microsoft for a reason. So Microsoft is pretty cool, but having said that, Google Colab is also pretty good. Google is a little new in the space today, and it gives you lots of freebies. If you're starting out on the personal note, I would say use Google Colab or Google Cloud Platform. It gives you lots of freebies at least to start with. You see, Flask and Django, Madhu, once again, they're web frameworks. They're a little aside from machine learning, so let's not get there. That's slightly different, and maybe that's totally into web development. Read a little bit about it. And basically, they're web frameworks. They're web frameworks. They help you in doing web development. Okay, they're web development libraries in Python. Think of it that way. Yeah. All right. Which project will we work? Atul, the project, again, the introduction to the project will happen in the next session. I wanted to give you a very basic overview of a generic data science life cycle. The specific project will be credit default dataset. I think I talked about that briefly, right? The exact datasets, other things we'll be sharing with you later. Exactly what to do, how to do will be the next session. We'll communicate that to you, how to go about it, okay? But it will be on credit dataset. How to extract important features if we don't know the target variable. Hey, target variable you must know, right, Surya? Hold on. Suppose you have to invest in a cap company and everything. Hold on. Okay. Which cap? Okay, which cap company you will choose for investment? Okay, which cap company you will choose for investment, Surya? But the target is still known, right? You want to predict the output. That is a cap company, right? It's a classification problem again, right? So naturally, your output has to be known. How can you not know the target variable? So ultimately, when you are saying I want to invest in a cap company, it's a classification problem, right? You want to choose which cap company you want to choose the investment. It's a classification problem technically, right? So from that perspective, naturally, from that perspective, yeah. Oh, okay. All right. See, logistic and random forest, Sunil, basically they're the same algorithms. Ultimately, they're both classification algorithms, right? So they both have similar metrics. Now, random forest only differences you can use for regression as well as for classification. How do you use them for evaluation metrics? That question, obviously it's the same thing, right? Confusion matrix is the same. Your accuracy, precision, recall, F1 score, RUC, AUC curve remains the same across both. You can pretty much use the same metrics, right? Unless you're using random forest for regression. That's the only difference, right? Yeah. All right. Okay, see, real time. Okay, hold on. See, I'll tell you one thing. Real time machine learning is something else. I must clarify this part. I think there are two types of machine learning. There is a batch machine learning. There's an offline, online machine learning. The kind of machine learning that we are mostly doing right now is offline machine learning, where you're building your models locally and then you're deploying them later. That is the primary thing we're working on right now. Real time online is something very different, which we'll typically implement at a different scale. Maybe Spark and all some of those things come in there. Okay, but the kind of machine learning we're primarily doing as part of the course is offline batch machine learning. Let me clarify that. Okay, real time AI is something very different. Okay, there's a fundamental difference between batch learning and online learning. So please be aware of the difference, all of you. Okay, yeah. How do we deal with data projects which are very less relevant data samples, Venkat? There are techniques like SMOTE. So I think, I'm not sure if you read about it or heard about it. There are undersampling and oversampling techniques that we actually use. There's something called SMOTE, synthetic minority oversampling technique. So class imbalance is also addressed using something called SMOTE. Read about something called SMOTE, synthetic minority oversampling technique. So that is also something that we use to handle class imbalance. And there are several different, there are several oversampling and undersampling techniques we use to address class imbalance. And that's one way to do it. The other way to address that is also to adjust your thresholds. So for example, logistic regression, the default threshold is 0.5, 50% threshold. What we can also do in that kind of a scenario is we can actually control our thresholds. Otherwise, accuracy is a very flawed metric, right? If you've got imbalanced class problem, accuracy is a flawed metric. I just want to take a few more questions just to do justice to the people who asked the questions, and then we'll take it off. All right, so sorry. Okay. Okay, see, I think, hold on. I think R is a very different piece. Let's not get there. R is probably going to be extended in the next 1 year. Okay, a lot of academia is still hellbent on R. In fact, if you go back a few decades, probably R was much more popular than Python. But if you talk about the current trend today, as I see in the industry today, and generally if I talk to people around, nobody uses R. Okay, nobody uses R. And all these languages, the primary reason why Python thrives is because of its community. There's a huge community around Python. It's open source. You need developers to constantly work on the modules, the open source modules, and there's not much development happening in R. Honestly speaking, what you have in sklearn today, scikit-learn, it's a beautiful library. All of it is combined in one place. You don't have anything nearly as same as in R. Because the carrot package is there. You have bits and pieces. but nothing as compact as sklearn, nothing as compact as TensorFlow and Keras that you have in Python. All right. Okay, so yes. Okay. I think that's fine. We can break. Yeah, I think we're not forcing you to stay back. I think I already clarified that. Taking up some additional questions. Sessions are recorded. All of you can drop out. Absolutely fine. I think I'm just taking some additional things, so you're absolutely free. How would it impact? Okay. All right. Okay. Yes, I think I took up that question as well. And let me just see, some other questions are coming up. Yes. Oh, okay. I'm. Hey, not really. I think that's okay. Okay. See, I'm just sharing my honest feedback. I think on R. I think see, again, the idea is obviously you know see, R, the concepts remain the same. The concepts don't change. I must clarify, the concepts don't change. Whether you learn it on R, on SAS, on SPSS, on whatever, doesn't matter. The concepts remain the same. Tomorrow, even if you go back and learn Spark, and Spark is again a very, very amazing thing you should all learn. Spark MLlib. That is the machine learning library of Spark. If you've got data distributed in a Spark cluster across multiple clusters, big data environment typically, it might happen that in your organization they're required to scale up on Spark. Believe me, after you've taken the course on R or Python, whatever, it will take you literally less than 1 weekend to scale up on Spark, because the libraries and the commands and the algorithms remain the same. Yeah, I will do that, Madhu. No problem. Yes, I'll do that. Yes. All right, cool. Okay. Hopefully, I've answered your questions. Okay. All right. So let's see. Am I missed out any questions, guys? It's really a pain to scroll all the way up to see your questions. So in case I've missed out anything, okay, let me know. Okay, use F1 score exactly. I think, Madhu, we can do that, absolutely. But then you must also go back and handle the class imbalance. Read about oversampling, undersampling. It's a beautiful technique. Okay, read about it a little bit. Then we'll discuss it in more detail when we come to the actual implementations in case studies. Okay, yeah. And polynomial regression will not help you too much. Okay, because I'll tell you what, Vijay. Polynomial regression, you're creating additional features. You're not creating additional rows, right? We're talking about imbalanced data set. It means rows are missing. Polynomial features will create new columns, not new rows, right? We're talking about creating new rows, new observations. Make sense? Yep. If you create more features and less data, that will be overfitting, right? That's another problem. Okay. All right. Yeah. Hope that answers your question. Yeah. Okay. Okay. Thank you so much, guys. I think I will do that. Couple of things I will share with you. I will nowadays JD datasets contain. You must scale up, Jay. You must. It's a very good point that you mentioned. I think you must scale up a little bit on NLP. NLP is one of the biggest things in machine learning and deep learning today. Because I'm working so extensively in the space, I can tell you that computer vision is a problem we have largely solved. Image processing, image recognition, all our CNN algorithms are pretty much been in existence for a long time. It's a problem we have largely mastered. Objects and images will not change, right? Elephants will look like elephants, buildings will look like buildings, cars will look like cars. We've got a very detailed labeled image data for that, and we have pretty much mastered that space. We are doing better. But then NLP is a space we are yet to conquer, right? And you only have to go back to Sundar Pichai's address last year, where he talked about where we talked about that haircut appointment, the very popular video that came out, and that particular thing is not deployed even today. And you can imagine the challenges in NLP even today, right? Most of organizational data, if you see, are still in textual format. Lots of documents, go back to all the paperwork. There are so many potential use cases in the legal domain that you have in this space, right? Legal domain. I mean, who reads those terms and conditions? There are pages long, hundreds of pages long. Go to a bank, try to open an account. You have to read that 20-page terms and condition document. Wouldn't it be amazing if you can have an application like InShorts, like what InShorts does, right? Summarize a 100-page news story into 60 words, something of that sort, right? So it's an amazing thing out there. We are still doing a lot of work in this space. NLP is a very, very big domain. And naturally, if you go for jobs right now, NLP is something people really ask for. Yes, we are not really testing on NLP in our project here. But then if you're interested, maybe in our discussions, we can talk a little bit about it. But for the specific case study we are doing as part of the sessions, we are definitely not testing on NLP. But deep learning NLP is something that you should definitely add to the repertoire. Deep learning, not so much because it's a different avenue altogether. You cannot obviously scale up, but NLP definitely you should do that. Yeah. Okay. Yeah. Very relevant, Gaurav. Let me clarify. to briefly address your question, if you're aware of a bit of deep learning, using convolutional neural networks, CNN, you can generate new features. You can generate new features using CNN. And now you can very much use your same existing SVM models or your same boosting bagging ensemble techniques after you generate new features. So yes, using neural networks, you can absolutely do predictions. You can absolutely do predictive analytics using deep learning. But another very common use case is that you can use neural networks to generate new features. Whatever feature extraction we talked about, PCA, polynomial features, you can use neural networks and specifically CNN. CNN stands for convolutional neural network. You can use CNNs to generate new features, and using those new features, you can now create your existing classical machine learning models. So they are pretty much relevant, and that hybrid way is still something that we tend to use quite a lot. Okay, just to answer your question, yes, it's very relevant. The hybrid form is still very useful today, even today, across organizations. All right. Okay, I think, yes. So thank you so much, guys. I think it's time to break, and it's been amazing interacting with all of you. So a lot of energy, lot of questions were asked. I think some questions I was not able to answer. So please forgive me for that. I think it's this. I think some of those people would have left also. It's too late, by the way. Anyways, please do come back in case anything went unanswered. Come back. Next session. Obviously, we are probably going to be meeting this weekend. Not sure. We're going to let you know, and we're going to meet again. And wish you all a very good night. Hopefully, all from India. Anyone from outside? Some of you said 1 a.m. Maybe the Singapore time is it? Maybe some Singapore or Malaysia joining in. Probably. Okay. So once again, thank you so much for your time, and take care, all of you. Okay. So do read this stuff. I'll be sharing all this with you. The PCA, the concrete one, which I discussed. I'll be sharing all these notes with you. So I think Stephen will reach out to you with these materials. So please revise these concepts. And initial session will be easy. It will be on SQL, primarily on SQL revision. And from there onwards, we'll be getting into machine learning, EDA, and we'll be looking at some of those pieces. Okay. All right. Wonderful. Thank you so much, guys. Take care, all of you. Bye-bye.
Thank you everyone for joining in on the session. Thank you so much, Sayan. That was really great. I think so many of the guys really, really loved it. Look forward to seeing everybody else in the future sessions, and speak to you guys soon. Take care. Please make
Bye-bye.
feedback once you're done.